space, an endless, mysterious expanse, holds answers to questions humanity has yet to grasp. It is not just the final frontier of physical exploration, but the ultimate domain of curiosity, searching for meaning and understanding in the cosmos. From the earliest moments when humans first gazed upward in awe at the night sky, we've felt an irresistible pull toward the stars, driven by a desire to understand not only the universe around us, but also our place within it. The universe, vast and incomprehensible, stretches beyond the limits of our understanding. Billions of galaxies, each containing countless stars and planets, serve as a testament to the sheer scale and complexity of nature. The observable universe, with its infinite stretches of time and space, calls us to embark on a journey that is as much about understanding the cosmos as it is about uncovering the very essence of our existence. We stand at the edge of the known, peering into an infinite ocean of stars, planets, and mysteries that stretch farther than we can imagine. As we journey deeper into the vastness, we are faced with questions that have lingered for centuries. What lies beyond the boundaries of our observable universe? Are we truly alone, or is the universe teeming with life, just waiting to be discovered? The universe, a boundless expanse encompassing all matter, energy, and time, is a cosmic puzzle. Scientists estimate its age at around 13.8 billion years, a figure that is continually refined with more precise observations. This estimation is grounded in evidence gathered from the motion of distant galaxies and the cosmic microwave background radiation, a faint echo from the Big Bang that marks the very beginning of our universe. From a singularity, a point of infinite density, the universe has expanded and evolved into the cosmos we observe today. Yet, despite our expanding knowledge, the universe remains largely enigmatic. Of the total composition of the cosmos, a mere 5% is composed of ordinary matter, the visible stars, planets, and galaxies that make up the universe we see. The remaining 95% consists of dark matter and dark energy, mysterious forces that we cannot directly observe but know exert a powerful influence on the universe. Dark matter, making up approximately 27% of the universe, acts as the unseen force that binds galaxies together. Dark energy, a much more elusive force comprising around 68%, is responsible for the accelerated expansion of the universe, a discovery that reshaped our understanding of cosmology and earned the Nobel Prize in Physics in 2011. As we look deeper into the universe, we cannot help but be drawn into questions that transcend the realm of science and touch the very fabric of philosophy. What is the true nature of existence? What are the origins of the universe? And what is its ultimate fate? The universe, with its untold mysteries, challenges us to confront questions that push the boundaries of both science and philosophy. Concepts like the multiverse theory, suggesting the existence of multiple universes, each with its own laws of nature, invite us to imagine the vastness of existence beyond our own cosmos. Could our universe be just one of countless others, each with its own unique characteristics? The quest to understand the age of the universe is a story that spans centuries of scientific exploration, from the earliest observations of the stars by ancient civilizations to the groundbreaking discoveries of the 20th century. It was in the 20th century that the concept of the universe's expansion took shape, with Edwin Hubble's 1929 discovery that galaxies are moving away from us, suggesting the universe itself is growing. This pivotal observation laid the groundwork for the Big Bang theory, which has become the leading explanation for the origin of the universe. Measuring the speed at which galaxies move away from us, what we now refer to as the Hubble constant, astronomers were able to estimate the rate at which the universe was expanding. However, the journey to understanding the true age of the universe was not straightforward. Early estimates of the Hubble constant suggested a younger universe, but as technology advanced and measurements became more refined, our understanding evolved. In the late 20th and early 21st centuries, new technologies like the Hubble Space Telescope and the Planck satellite provided unprecedented data. The Planck satellite in particular played a pivotal role in refining our knowledge of the cosmic microwave background radiation. This radiation, the afterglow of the Big Bang, offered a clearer picture of the universe's early moments, allowing astronomers to narrow down the value of the Hubble constant and refine the estimate of the universe's age. Today, The best estimate stands at about 13.8 billion years. Through this journey of discovery, we have not only unlocked new knowledge about the cosmos, but also deepened our understanding of the profound mysteries that lie at the very heart of our existence. Space, with all its vastness and complexity, continues to challenge our perceptions, offering new frontiers for exploration and understanding. The determination of the universe's age is a story woven into the fabric of time itself, and it's not just the telescopes that help us see across the eons. It's the stars, the brilliant burning beacons of our universe that guide us through the depths of cosmic history. By studying the life cycles of stars, particularly the oldest ones within globular clusters, astronomers have been able to establish the minimum age of the universe. These globular clusters are dense groups of stars held together by the force of gravity, which act as cosmic time capsules. Some of the stars in these clusters are among the first to have formed after the Big Bang, offering us what can be likened to a stellar clock, marking the passage of time. The oldest of these stars, nearly 13 billion years old, are remarkably close to the age of the universe itself, providing a critical lower limit to our cosmic timeline. And yet, as we explore further into the universe's vast expanse, we encounter a concept that fascinates the mind: the observable universe. This isn't just about the stars we can see with our naked eye or through telescopes. It's about the portion of the universe that we can detect, limited by the speed of light and the age of the cosmos. Because light travels at a finite speed of approximately 299,792 kilometers per second, it takes time for light to reach us from distant objects. The observable universe, therefore, is the spherical region centered on Earth, extending outward to a radius of about 46.5 billion light-years. This boundary represents the farthest distance from which light has had time to travel since the birth of the universe, roughly 13.8 billion years ago. The light that reaches us from these far-flung regions provides a snapshot of the universe's early years, offering a glimpse into its evolution. However, a crucial distinction must be made between the observable universe and the entire universe. The observable universe is what we can see. The entire universe, on the other hand, stretches far beyond what we can currently detect. In fact, the true extent of the universe remains a mystery, possibly extending infinitely or curving back upon itself in ways that defy conventional geometry. Within the observable universe, we can find an estimated 2 trillion galaxies, each teeming with millions or even trillions of stars, not to mention an even greater number of planets, moons, asteroids, and comets. This staggering number isn't speculative. It's based on deep sky surveys and observations made by telescopes like the Hubble Space Telescope, which has allowed us to peer back in time and witness the universe as it was shortly after its inception. These observations are far more than just numbers. They have illuminated the vastness of the cosmos, unveiling the formation and evolution of cosmic structures. But there's more to our understanding of the universe than just counting galaxies. To truly comprehend the observable universe, we must confront complex theories like cosmic inflation. This theory suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching the very fabric of space itself. This rapid growth created the vast distances we now observe between galaxies, and provides an explanation for phenomena such as the uniformity of the cosmic microwave background radiation and the large-scale distribution of galaxies. As we continue to explore the observable universe, we are confronted with the limitations of both our technology and the laws of physics. There are regions of space beyond the observable universe where light has not had enough time to reach us. This means that these areas remain forever out of sight, at least with our current methods of observation. But even with these limitations, our ability to observe and understand the cosmos continues to evolve. Advances in telescope technology and observational techniques are continually pushing the boundaries of what we can see, providing us with ever clearer views into the structure of the universe, its history, and the fundamental laws that govern it. So, how do we observe this vast expanse? Observing the universe is no small task, and it involves a wide array of instruments, each designed to capture different facets of cosmic phenomena. Central to this endeavor are telescopes, which have undergone incredible advancements over the centuries. From Galileo's rudimentary optical telescopes to the highly sophisticated observatories we use today, these instruments have allowed us to probe the depths of space, detecting not just visible light, but a range of electromagnetic radiation. Modern telescopes can capture radio waves, infrared light, ultraviolet rays, X-rays, and even gamma rays, each one revealing a different layer of the cosmic landscape. Optical telescopes, which collect visible light, have been the cornerstone of our initial efforts to observe the stars, galaxies, and nebulae within the observable universe. However, to fully understand the complexity of the universe, we've had to expand our view beyond the visible spectrum. Radio telescopes, for example, have unveiled phenomena invisible to optical telescopes, such as the cosmic microwave background radiation, a remnant from the early universe, providing critical evidence for the Big Bang theory. Infrared telescopes, meanwhile, allow us to observe celestial objects that are hidden from view by thick clouds of dust. They've revealed the formation of new stars and distant galaxies that were previously obscured. But the universe isn't just about what we can see in the visible and infrared spectra. High-energy phenomena, like black holes and neutron stars, are some of the most extreme events in the cosmos. And to study them, we need X-ray and gamma-ray telescopes. These instruments provide a glimpse into the violent and energetic processes occurring in these cosmic regions, offering new insights into the forces at play in the universe's most intense environments. Space-based telescopes like the Hubble Space Telescope represent a leap forward in our observational capabilities. Orbiting beyond the distorting effects of Earth's atmosphere, these instruments can capture clearer, more detailed images, providing an unobstructed view of the universe. Hubble, in particular, has revolutionized our understanding of the cosmos, providing breathtaking images of distant galaxies, nebulae, and even planets within our own solar system. As we continue to refine our technology and push the boundaries of our observational power, the universe's secrets slowly begin to reveal themselves. But even as we gaze deeper into the cosmos, we're reminded that there is still much we don't know. The universe, vast and mysterious, continues to unfold before our eyes, and each new discovery brings us closer to understanding the nature of space, time, and our place within it. The James Webb Space Telescope, JWST, launched to succeed the iconic Hubble, marks a monumental leap in our ability to explore the universe. Focusing primarily on infrared astronomy, the JWST's mission goes far beyond Hubble's visible light observations, aiming to peer deeper into the cosmos to uncover the formation of the first galaxies, stars, and planetary systems. It opens a window into the universe's past, enabling us to witness the events that unfolded in the earliest moments after the Big Bang, a time previously beyond our reach. Yet the quest for knowledge about the universe does not stop at visible or infrared light. As science continues to evolve, new and innovative methods of observation have emerged. Neutrino observatories, like those scattered across the globe, capture the nearly massless particles from space that provide invaluable insight into the workings of our sun and the violent explosions of supernovae. These neutrinos hold secrets to some of the most profound processes in the universe, offering a view into the fundamental forces that govern our cosmos. Meanwhile, gravitational wave observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, have unlocked an entirely new way to study the universe. By detecting ripples in space-time itself, caused by cataclysmic events like the merging of black holes or neutron stars, LIGO allows us to observe phenomena that emit little to no light. This method of exploration offers a fresh perspective, one where the very fabric of space-time is disrupted. And through this disturbance, we glean information about some of the most extreme events in the universe. Despite the remarkable advances made in cosmic observation, one question continually arises: why can't we see beyond the observable universe? This question not only strikes at the heart of astronomy, but also addresses the very nature of the universe itself. The observable universe is the region of space that is within our light reach, the farthest distances from which light has had time to travel since the universe began, roughly 13.8 billion years ago. However, this limit is not a tangible boundary, but a consequence of the finite speed of light and the age of the universe. Light travels at a constant speed of 299,792 kilometers per second in a vacuum, setting a universal speed limit. Since the universe itself is 13.8 billion years old, the farthest light we can detect originates from a distance that corresponds to that age. Yet, because the universe has been expanding since the Big Bang, the observable universe extends to about 46.5 billion light years. Beyond this distance, light from more distant regions has not yet had enough time to reach us. This distant, unreachable realm is what we call the unobservable universe. As if this challenge weren't enough, the expansion of the universe, driven by the mysterious force of dark energy, accelerates the recession of galaxies. As galaxies move further away from us, their speed increases with distance. Eventually, this expansion outpaces the speed of light, creating a cosmic horizon that further limits our view of the universe. This phenomenon does not violate Einstein's theory of relativity because it's not objects within space moving faster than light, but the fabric of space itself stretching. The observable universe is also deeply tied to the theory of cosmic inflation, a brief but incredibly rapid expansion in the universe's first moments. This inflationary period stretched the very fabric of space-time itself, sending regions far beyond our current reach. Regions so distant their light will never be able to reach us, thereby limiting the observable universe's size. In addition to distance, the concept of time also shapes the observable universe. Observing the farthest reaches of space is akin to looking back in time. The further we look, the older the light we receive, until we finally reach the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This radiation represents the earliest light we can observe, which is why it marks the boundary of time's reach in the universe. Beyond it lies a period known as the Cosmic Dark Ages, a time before the first stars ignited and starlight began to fill the universe. As we venture deeper into the cosmos and seek to unravel the mysteries that lie beyond our current observational reach, astronomers employ a variety of increasingly sophisticated tools to peer further into space and time. Each instrument is designed to capture unique information across different wavelengths of light, from visible to infrared to radio waves. These instruments, working in concert, give us an unprecedented view of the universe. At the forefront of astronomical observation are telescopes. Optical telescopes, which collect visible light, have long been the cornerstone of astronomy. From ground-based observatories to space telescopes like Hubble, these tools allow us to observe everything from nearby planets to distant galaxies. Yet visible light is only one piece of the puzzle. Much of the universe's information is invisible to the naked eye, hidden in wavelengths of light that lie outside the visible spectrum. Radio telescopes have revolutionized our understanding of the cosmos, providing the ability to observe regions of space that are cold and dark, such as gas and dust clouds where new stars are being born. Instruments like the Very Large Array in New Mexico or the Atacama Large Millimeter Submillimeter Array in Chile can detect the faintest radio signals emitted by distant galaxies, giving astronomers a glimpse into the early stages of the universe's evolution. These discoveries allow us to trace the origins of cosmic structures, the remnants of the Big Bang, and the birthplaces of stars. With each new technological advancement, our understanding of the universe deepens. The limits of our observation may be defined by the speed of light, the expansion of space, and the nature of cosmic time, but they are also shaped by our relentless curiosity and technological ingenuity. As we continue to push the boundaries of what is observable, we move closer to answering some of the most profound questions about the origins of the universe, the nature of space and time, and the forces that shape everything we see. The universe, it seems, is vast, and we are only just beginning to glimpse its true extent. In the vast expanse of the universe, infrared telescopes, like the Spitzer Space Telescope, cut through thick cosmic dust clouds, unveiling star clusters and distant galaxies that remain hidden to the naked eye. These observations give astronomers profound insights into the birth of stars and the early stages of the universe's evolution. Meanwhile, X-ray and gamma-ray observatories, such as the Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope, delve into the universe's most extreme and energetic phenomena. They illuminate the mysteries of black holes, neutron stars, and supernovae, unveiling the explosive forces and extraordinary events occurring in deep space. However, the journey into the cosmos does not end with electromagnetic radiation alone. Gravitational wave detectors like LIGO and Virgo have opened an entirely new realm of observation. These instruments detect ripples in spacetime caused by the violent mergers of black holes and neutron stars, marking the dawn of multi-messenger astronomy. By combining gravitational wave signals with traditional electromagnetic observations, astronomers can now weave a more complete tapestry of cosmic events, enhancing our understanding of the forces shaping the universe. In addition, neutrino observatories like the Ice Cube Neutrino Observatory located beneath the Antarctic ice offer an invaluable perspective by detecting nearly massless neutrinos. These elusive particles, which travel unhindered across the universe, provide clues to some of the most intense astrophysical processes, including solar fusion and the cataclysmic explosions of supernovae. The pursuit of knowledge about the cosmos is not limited to Earth-based instruments alone. And interplanetary missions, such as the Voyager probes, New Horizons, and the Mars rovers, serve as our eyes and ears in space. These spacecraft venture into the unknown, delivering detailed images and data about the planets, moons, and celestial bodies within and beyond our solar system. They extend our reach and deepen our understanding of the distant worlds that orbit our sun, offering clues about the origins of our own planet and the possibility of life elsewhere. In unison, these diverse tools of exploration and observation provide an unprecedented view of the cosmos, allowing astronomers to construct a fuller, more integrated understanding of the universe's structure, its origins, and the laws governing its evolution. From the most energetic phenomena to the farthest reaches of space, our ability to observe the universe has grown exponentially, leading to discoveries that have revolutionized our view of existence itself. Looking back over the centuries, our understanding of the universe has transformed dramatically, evolving from mythological and philosophical speculations to an empirical, data-driven exploration of the cosmos. In ancient times, early civilizations viewed the universe through a lens of mythology and observation. The Greeks, for instance, conceived of the heavens as a crystal sphere surrounding the Earth, with stars fixed upon this celestial vault. This geocentric model, placing Earth at the center of the universe, dominated thought for centuries, influencing Western civilization's understanding of the cosmos. It wasn't until the 16th and 17th centuries, with the groundbreaking work of Nicholas Copernicus, that a revolutionary idea began to take hold. The sun, not the Earth, was at the center of the universe. This heliocentric model was a seismic shift in astronomical thought. The subsequent work of Johannes Kepler and Galileo Galilei provided the evidence needed to support Copernicus's theory, challenging centuries of belief and sparking the scientific revolution. Galileo's invention of the telescope allowed him to make critical discoveries, such as the moons of Jupiter and the phases of Venus, which further debunked the geocentric model and laid the foundation for modern astronomy. As telescopic technology continued to advance, so too did humanity's understanding of the cosmos. The 18th and 19th centuries brought the discovery of new planets within our solar system, while the 20th century marked a monumental breakthrough. Edwin Hubble's observations confirmed that galaxies extend far beyond our own Milky Way, revealing that the universe is not static, but expanding. This discovery provided crucial support for the Big Bang theory, proposing that the universe had a definitive beginning, a concept that would dominate our understanding of cosmic origins. The latter half of the 20th century and the early 21st century brought further breakthroughs. The advent of space telescopes and advanced ground-based observatories expanded our understanding even more. Instruments like the Hubble Space Telescope and the Large Hadron Collider have allowed us to peer deeper into the universe, revealing phenomena such as exoplanets, cosmic microwave background radiation, and the mysterious forces of dark matter and dark energy. These discoveries are key to understanding the makeup of the universe, where ordinary matter, everything we know and see, constitutes only a small fraction of its total mass energy content. At the heart of this ever-evolving knowledge is the lambda CDM model, which explains that the universe is dominated by dark energy and dark matter, with the visible matter playing only a minor role. This model suggests that the universe, 13.8 billion years old, is constantly expanding, with galaxies scattered across vast cosmic distances, each telling its own story in the grand narrative of the universe's ongoing evolution. From early myths to modern science, humanity's quest to understand the cosmos is one of our most profound journeys, an ongoing exploration that continues to push the boundaries of what we know and what we are capable of discovering. The evolution of our understanding of the universe is nothing short of a triumph of human curiosity, a testament to our relentless pursuit of knowledge. It is a story that has moved beyond ancient Earth-centered models, venturing into an awe-inspiring cosmos, vast and expanding. In this vastness, Earth is but a minuscule speck in an incomprehensible expanse of stars, galaxies, and cosmic phenomena. But what sparked this journey of discovery, and how did we come to grasp the monumental scale of space? When it comes to exploring the cosmos, the term light year holds an essential role. It's a crucial bridge in our comprehension of the vast distances between celestial bodies. Yet, contrary to what one might assume, a light year is not a unit of time, but a measure of distance. It defines the length light travels in one Earth year, yes, hurtling at a constant speed of about 299,792 kilometers per second, 186,282 miles per second, through the vacuum of space. In 1 year, light can travel an astonishing 9.46 trillion kilometers, 5.8 trillion miles. This mind-boggling distance allows astronomers to convey the expansive separation between stars, galaxies, and the myriad wonders of the universe, bringing them into more understandable terms for the human mind. The reason the light year is so essential lies in its ability to provide a standard unit of measurement that encapsulates the immensity of the cosmos in a way that is digestible to human cognition. Take Proxima Centauri, for example, the closest known star to the Sun, located 4.37 light years away. This means the light we see from this star today embarked on its journey across space 4.37 years ago. This concept beautifully intertwines the idea of time with space, revealing the dynamic nature of the universe. It is not just a snapshot of a distant star, but a fleeting moment, a connection between our present and the past. But why is the light year so integral to our understanding of the universe's structure? At its core, the light year is rooted in the very fabric of physics and astronomy. The speed of light, a fundamental constant in nature, is a pillar of Albert Einstein's theory of relativity. It provides a stable foundation for measuring cosmic distances across the vast expanse of space. This consistency makes the light year not only a universal metric, but also one that connects different observations and theories in astrophysics and cosmology. When astronomers announce that a galaxy is 100 million light years away, the enormity of this figure instantly sparks our understanding of how far and how long it took for light to travel that distance, showing us not only spatial relationships, but also a glimpse into the history of the universe itself. As we peer deeper into the cosmos, we can trace the formation and evolution of galaxies, an intricate tale spanning billions of years. It all began shortly after the Big Bang, an explosive event that marked the birth of the universe some 13.8 billion years ago. The universe was initially a seething, hot, and dense plasma of particles and radiation. As it expanded and cooled, matter began to coalesce under the influence of gravity, paving the way for the formation of galaxies. The earliest galaxies emerged from small fluctuations in the density of the universe's primordial matter, tiny ripples in space-time that were amplified by the gravitational pull of dark matter. These clumps of matter drew in ordinary matter, cooling and collapsing into gas clouds that eventually formed the first stars. This period, known as the Cosmic Dawn, saw the birth of proto-galaxies, marking the beginning of galaxy formation. Galaxies evolve over time through various processes. One of the main drivers of this evolution is star formation. Within a galaxy, dense clouds of gas and dust collapse under gravity, initiating nuclear fusion in their cores and giving rise to new stars. These stars go through life cycles, from their fiery births to their explosive deaths in supernovae. In their death throes, stars release heavy elements into the surrounding gas, which, in turn, fuels the formation of new stars, enriching the galaxy chemically. Another crucial mechanism in galactic evolution is the merging of galaxies. Galaxies are not isolated entities. Gravity pulls them together, and collisions often occur. These cosmic mergers can dramatically reshape galaxies, turning spirals into ellipses and even sparking bursts of new star formation. The Milky Way itself is on a collision course with the Andromeda Galaxy. In approximately 4 billion years, the two will merge, a reminder that galaxies are dynamic and constantly evolving. Through their lifetimes, galaxies undergo a series of transformations. They may collide and merge with others, or they may strip gas from neighboring galaxies. Some may evolve in isolation, slowly converting their gas into stars over time. Central black holes, the unseen giants at the heart of many galaxies, also play a significant role. These cosmic behemoths can trigger or suppress star formation, further influencing the shape and fate of galaxies. The study of galaxy formation and evolution is a rich and dynamic field, constantly evolving as new observations and advanced simulations shed light on the universe's complex history. Telescopes across the electromagnetic spectrum, paired with cutting-edge computer models, enable scientists to piece together the story of galaxies, from their origins in the smooth, nearly uniform cosmos post-Big Bang to the intricate, diverse structures we see today. In this journey of discovery, the universe reveals itself not as a static entity, but as a living, breathing tapestry, constantly shifting, expanding, and evolving. Each light year, each star, each galaxy offers a piece of the grand puzzle that we as humans are still striving to comprehend. As our understanding deepens, so too does our appreciation of the boundless wonders of the cosmos, an ever-expanding story of exploration and discovery that is, at its heart, driven by the unyielding curiosity of the human spirit. Within the vast expanse of our universe, the so-called superclusters stand as monumental testaments to the awe-inspiring scale and complexity of the cosmos. These colossal formations, stretching across hundreds of millions of light years, are not merely clusters of galaxies, but intricate networks that reveal the hidden structures binding the universe together. They are composed of interconnected galaxies and galaxy clusters, each woven together by invisible strands of dark matter, forming an intricate web of cosmic architecture. However, it is not only the sheer size of superclusters that makes them significant. Their very existence unveils profound insights into the structure of the universe itself. At the heart of their importance lies the revelation of how matter is distributed throughout space, as well as how the gravitational forces shaped by dark matter mold the cosmos over vast stretches of time. Superclusters are central to our understanding of the universe's large-scale structure, providing a key to deciphering the cosmic puzzle. These immense structures emerge at the intersection of cosmic filaments, the very framework of the cosmic web, an enormous network of dark matter stretching across the universe. The formation of superclusters is a direct result of the minute fluctuations in density present in the early universe, amplified over billions of years by the relentless gravitational pull of dark matter. It is through the study of these superclusters that we are able to trace the universe's evolution, gaining invaluable insights into the nature of dark matter itself and how the universe has expanded since the dawn of time. One of the most famous examples of a supercluster is the Laniakea supercluster, which includes the Milky Way among its tens of thousands of galaxies. Spanning approximately 500 million light years, Laniakea's discovery served as a profound reminder of the interconnectedness of galaxies within the universe, and it revealed the true scale of cosmic structures we once thought were far beyond comprehension. The gravitational flows of galaxies towards the dense regions of superclusters underscore the dynamic and ever-evolving nature of the universe, with galaxies constantly in motion, shaping and reshaping one another within this vast, intricate structure. Superclusters are not merely relics of the past. They are living, breathing entities that play a pivotal role in the study of cosmology, the science of the universe's origin, structure, evolution, and ultimate fate. The distribution, mass, and movement of superclusters hold the key to understanding the geometry of the universe itself and how it has expanded over time. Furthermore, observations of these massive structures provide crucial evidence for the existence of dark energy, the mysterious force accelerating the expansion of the universe, helping astronomers refine their models of cosmic evolution. In addition to their role in cosmology, Superclusters are invaluable laboratories for studying galaxy evolution on the grandest scales. The environments within superclusters vary dramatically, from the dense, energetic centers of galaxy clusters to the isolated galaxies scattered along their fringes. Each of these environments presents unique conditions that influence the formation of stars, the interactions between galaxies, and the growth of supermassive black holes. By observing how galaxies evolve in these diverse environments, astronomers gain a deeper understanding of the processes that shape galaxies and the role their surroundings play in their development. The term cosmic web captures the breathtaking intricacy of the universe's large-scale structure. This vast network of interconnected galaxies and galaxy clusters is linked together by invisible strands of dark matter, creating a structure that envelops the universe. These cosmic strands stretch across millions of light years, surrounding vast voids where galaxies are few and far between. This grand web is the universe's largest scale structure, shaped by the uneven distribution of matter that originated with the Big Bang and sculpted over billions of years by the gravitational pull of dark matter. The cosmic web story begins in the earliest moments of the universe, when quantum fluctuations created slight variations in density across the primordial soup of particles. As the universe expanded, these fluctuations grew, amplified by the gravitational influence of dark matter. The regions of higher density formed the galaxies and clusters we observe today, while the areas of lower density evolved into the voids, vast expanses of emptiness that punctuate the otherwise intricate fabric of the cosmos. The key to understanding the cosmic web lies in the nature of dark matter, an invisible substance that accounts for roughly 27% of the universe's total mass and energy. Though dark matter cannot be seen directly, its presence is inferred through its gravitational effects on visible matter. This dark matter has played a crucial role in shaping the cosmic web, drawing matter into the dense regions that would eventually form galaxies and clusters, and leaving behind the vast empty voids. Cosmic surveys such as the Sloan Digital Sky Survey, SDSS, have mapped the distribution of galaxies across enormous stretches of space, revealing the astonishing detail of the cosmic web. These surveys have shown that galaxies are not scattered randomly throughout the universe, but instead align along vast filaments, connecting at massive nodes where galaxy clusters reside. The cosmic web is a dynamic, ever-evolving entity, with galaxies constantly moving along the filaments, drawn toward the gravitational wells of galaxy clusters. Studying the cosmic web provides crucial insights into several aspects of cosmic evolution. It helps us understand the role of dark matter in shaping the universe, the process of galaxy formation, and the distribution of matter across the cosmos. Furthermore, these studies offer key evidence for the presence of dark energy, which is believed to be responsible for the accelerating expansion of the universe. As our knowledge deepens, the cosmic web continues to reveal the mysteries of the universe, offering clues to the forces that govern the cosmos on its largest scales. At the very heart of the universe's evolution are the enigmatic black holes, massive entities where gravity is so intense that even light cannot escape. These cosmic giants play a central role in the formation and dynamics of galaxies, influencing everything from the birth of stars to the distribution of matter across the universe. The fascination with black holes lies not just in their mysterious nature, but in the significant impact they have on the universe itself. Most large galaxies, including our own Milky Way, harbor supermassive black holes at their centers. These monstrous objects, with masses ranging from millions to billions of times that of the Sun, are not merely remnants of cosmic cataclysms, but active, influential players in galactic evolution. The energy emitted by these black holes, especially during the mergers of galaxies, has profound effects on their surrounding environments. As galaxies collide and merge, their central black holes also combine, unleashing immense bursts of energy that ripple through space, potentially shaping the very structure of the universe. Black holes also play a pivotal role in powering some of the brightest objects in the universe, such as quasars and active galactic nuclei, AGN. These luminous beacons, visible across vast cosmic distances, not only illuminate the intergalactic medium, but also influence the formation of galaxies along the cosmic web. Through their powerful emissions, black holes help shape the very fabric of the universe, influencing the evolution of galaxies and the distribution of matter in profound and enduring ways. In the vast and ever-expanding cosmos, feedback mechanisms from active galactic nuclei, AGN, play a pivotal role in shaping the universe as we know it. As energy is injected back into the surrounding gas, star formation within galaxies is halted, profoundly impacting the large-scale structure of the universe. This process doesn't just halt stars, it influences entire galaxies, shaping their evolution and altering the cosmic fabric. But it doesn't stop there. The groundbreaking detection of gravitational waves from merging black holes in 2015 opened an entirely new window to explore the cosmos. These ripples in space-time, detected for the first time by the Laser Interferometer Gravitational Wave Observatory, LIGO, have provided us with a novel way to probe the deepest corners of the universe. Through gravitational wave astronomy, we gain insight into the black hole population and their intricate role in the universe's evolutionary journey. Gravitational waves allow scientists to map the distribution of black holes across the cosmic web, further enhancing our understanding of the universe's architecture. The study of black holes, however, is not merely about mapping cosmic objects. It ventures into the heart of some of the most fundamental questions concerning space-time and the nature of the universe. Theories that attempt to unify quantum mechanics with general relativity, such as string theory and loop quantum gravity, see black holes as testing grounds for new ideas. These cosmic giants challenge our understanding of gravity, space-time, and even the ultimate fate of the universe itself. One of the most puzzling questions in modern physics is the information paradox. How can information be preserved in a universe that contains black holes? This paradox holds the potential to unravel some of the deepest mysteries of the universe's laws. Black holes are much more than celestial oddities. They are at the very core of the universe's structure and dynamics. From anchoring galaxies to shaping the cosmic web and providing clues to the fundamental forces of nature, black holes are indispensable in our quest to understand the cosmos. Now let's turn our attention to another key component of the universe's structure: voids. Voids in space, far from being empty expanses, are integral to understanding the universe's large-scale architecture. These cosmic voids are like the blank spaces in a painting, defining the structure of the cosmos by outlining the areas where galaxies do not exist, just as clusters and superclusters show us where galaxies are densely packed. These voids support key theories in cosmology, including cosmic inflation and the distribution of dark matter. The uneven distribution of matter, a result of quantum fluctuations in the early universe, has given rise to the voids we see today. Despite their name, voids are not truly empty. They contain galaxies, albeit far fewer than the denser regions of space, and these galaxies are generally smaller, less luminous, and less massive. Studying these isolated galaxies provides valuable insights into galaxy formation and evolution, offering a view of galactic development free from the gravitational complexity found in denser environments like galaxy clusters. The discovery and mapping of voids have been made possible thanks to large-scale galaxy surveys that meticulously chart the positions of galaxies across the cosmos. These surveys reveal the intricate filamentous structure of the cosmic web, with vast voids stretching across the universe, separating these filaments. Voids come in various shapes and sizes, with the Boat's void, the largest known void, spanning a colossal 330 million light-years. And contrary to what we might expect, these voids are not static. They expand over time, driven by the repulsive force of dark energy, as the universe itself continues to stretch and evolve. Studying these voids offers a unique perspective on the universe's expansion, providing critical clues about the nature of dark energy and the universe's fate. Since voids occupy the majority of the universe's volume, understanding their dynamics is essential to formulating a complete picture of cosmic history. Moreover, their size and distribution allow cosmologists to test different models of the universe, offering valuable constraints on the properties of dark matter and dark energy. The concept of the edge of the observable universe brings us to the outermost limits of our understanding. This boundary marks the farthest regions of the universe from which light has had enough time to reach us since the universe's birth around 13.8 billion years ago. It is not a physical boundary, but a horizon determined by the speed of light and the universe's age. The observable universe, centered around Earth, has a radius of approximately 46.5 billion light-years, a number that may seem puzzling given the universe's age. The apparent discrepancy arises due to the expansion of space itself. As the universe stretches, it carries distant light with it, pushing the observable universe further out than the mere product of the universe's age and the speed of light would suggest. This expanding boundary is not fixed. It recedes continually as light from more distant parts of the universe reaches us. However, it is crucial to remember that this boundary does not represent the universe's physical edge. There is far more beyond this horizon, potentially an infinite expanse filled with galaxies, stars, and cosmic entities that remain out of reach. This concept ties closely to the inflationary model of the universe, which suggests that shortly after the Big Bang, the universe underwent a period of rapid exponential expansion. This inflationary phase pushed vast regions of space beyond our observational reach, contributing to the immense size of the unobservable universe. It serves as a powerful reminder of the universe's dynamic and ever-evolving nature. The edge of the observable universe, however, is not merely a spatial boundary, it is also a temporal one. As we look farther into the cosmos, we are effectively looking backward in time, observing the universe as it was in its infancy. The light that reaches us from the very edge brings with it crucial information from the early universe, glimpses of the first galaxies, the formation of cosmic structures, and the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. These observations are not only fascinating, they are critical to our understanding of the universe's origins, composition, and ultimate destiny. At the very frontier of this observable universe lies a treasure trove of cosmic mystery. This boundary, a staggering 46.5 billion light-years away, represents the furthest we can peer into the universe. Here, at the edge of the known cosmos, we witness the remnants of the universe's earliest moments. The oldest light we can detect, the CMB radiation, provides us with an invaluable window into the birth of the universe itself, offering clues to its age, composition, and eventual fate. The universe, it seems, is a vast and mysterious place, and with each discovery, we are slowly beginning to uncover its secrets. As we push the boundaries of our knowledge, one thing becomes clear. The more we learn, the greater the cosmic mysteries become. But as we look deeper into the universe, the cosmos unfolds a vast and mysterious story, starting with the cosmic microwave background, CMB radiation. This afterglow of the Big Bang, an imprint left over from a time when the universe was just 380,000 years old, marks the moment when the universe became transparent to light. Before this moment, the universe was a hot, dense plasma filled with electrons, protons, and photons. Light particles, photons, were constantly absorbed and re-emitted by these particles, creating an opaque universe. As the universe cooled and expanded, atoms began to form when protons and electrons combined. This allowed photons to travel freely across space. The radiation we detect today, the CMB, is this very light but stretched to microwave wavelengths due to the universe's ongoing expansion. When we observe this ancient light, we're essentially peering into a time long before galaxies, stars, or planets existed, when the universe was in its most uniform state. The tiny temperature fluctuations in the CMB reveal minute differences in density, which would become the seeds for all future cosmic structures, our galaxies, stars, and even our own planet. The study of the CMB is vital in cosmology, as it provides empirical evidence supporting the Big Bang theory. By analyzing the CMB, scientists can determine fundamental aspects of the universe, such as its age, rate of expansion, and its composition. These insights have been critical for refining our understanding of the universe's origins and shaping models of its evolution. However, beyond the CMB lies an uncharted territory, the space beyond the observable universe, which enters the realm of speculation. The universe, it seems, may extend infinitely beyond what we can see, filled with galaxies and stars similar to those in our observable universe. But because light from these distant regions has not yet had time to reach us, these parts of the cosmos remain beyond our current ability to detect or study directly. This concept of the edge of the observable universe is not a physical boundary. Rather, it is a limit dictated by the speed of light and the finite age of the universe. As we peer further out into space, we are also looking further back in time. The observable universe represents the earliest moments we can study, with the cosmic microwave background radiation marking the farthest and oldest light we can observe. Beyond this, the universe remains a mystery. Still, we can infer from the CMB that the universe likely continues, brimming with undiscovered structures and phenomena waiting to be explored. The expanding universe is crucial to understanding what we can see and comprehend about the cosmos. This expansion means the very fabric of space itself is stretching, pushing galaxies away from one another over time. As galaxies move apart, the light from these galaxies is also stretched, a phenomenon known as redshift. The further a galaxy is, the more its light is stretched, and the faster it seems to recede from us. This relationship is encapsulated by Hubble's law, named after Edwin Hubble, who observed this expansion in the 1920s. The expansion of the universe not only affects the light we see, but also determines the size of the observable universe. The cosmic light horizon marks the furthest distance from which light has had time to reach us, a boundary defined by the finite age of the universe, about 13.8 billion years. As the universe expands, this horizon stretches, allowing us to see light from even farther away. Yet, this same expansion means that some regions of the universe are receding from us so rapidly that their light will never reach us, pushing them beyond our observational reach. The future of our ability to observe the universe is also influenced by this expansion. As the universe continues to accelerate, driven by the enigmatic force known as dark energy, galaxies beyond our local group, the Milky Way and its nearest neighbors, will eventually drift beyond our cosmic horizon. Their light will no longer be able to reach us, making them invisible and isolated from our observable universe. In essence, we are witnessing the shrinking of our observable universe as the cosmos continues to expand. Moreover, this expansion directly impacts the cosmic microwave background radiation. As the universe expands, the CMB's wavelength stretches, causing the radiation to cool and fade, making it more challenging to detect over time. This phenomenon further underscores the delicate balance between expansion and observation in the study of the universe. The CMB also plays a critical role in confirming the Big Bang theory. Before its detection in 1965 by Arno Penzias and Robert Wilson, the origin of the universe was a subject of intense debate. The discovery of the CMB provided the first solid evidence of the Big Bang, fundamentally altering our understanding of how the universe began. Beyond its confirmation of the Big Bang, the CMB is invaluable for mapping the early universe in remarkable detail. Minute temperature fluctuations within the CMB, often as small as 1 part in 100,000, reveal the density variations that existed in the primordial universe. These variations set the stage for the formation of galaxies, clusters, and superclusters. By studying these fluctuations, scientists can infer the distribution of matter and energy in the early universe, shedding light on how cosmic structures evolved over billions of years. The CMB has also been instrumental in refining our knowledge of the universe's fundamental parameters, such as its age, shape, and composition. Additionally, measurements of the CMB have solidified our understanding of the universe's flatness on large scales and help provide precise estimates of its age. Perhaps most intriguingly, the CMB offers insights into dark matter and dark energy, two of the most mysterious and elusive components of the universe. Together, dark matter and dark energy make up approximately 95% of the universe's total mass energy content, and the CMB provides one of the most direct ways to study their effects. Through careful analysis, scientists have uncovered clues about the nature and distribution of these enigmatic forces, which continue to shape our understanding of the cosmos. The CMB also touches on the very foundations of physics. Subtle patterns and asymmetries within the CMB challenge and refine our understanding of the universe's fundamental forces. These patterns have profound implications for inflation theory, which proposes a period of rapid expansion in the universe's earliest moments. Inflation theory suggests that the universe underwent an exponential growth spurt just fractions of a second after the Big Bang, smoothing out irregularities in the universe's density. However, the tiny fluctuations observed in the CMB offer strong evidence that, despite this rapid expansion, slight irregularities remained, laying the groundwork for the universe we observe today. Looking out to the edge of the observable universe presents numerous challenges. The vast distances, the faintness of distant light, and the complex nature of cosmic phenomena all contribute to the difficulty in studying the farthest reaches of the universe. Yet, despite these obstacles, scientists continue to push the boundaries of our knowledge, developing new tools and techniques to explore the cosmos and unravel its deepest secrets. In this cosmic journey, the edge of the observable universe remains both a frontier and a profound mystery, a boundary that marks the limits of what we can know, yet hints at the boundless possibilities that lie beyond. The observable universe extends an astonishing 46.5 billion light-years from Earth, a staggering distance that light has traveled since the universe's birth, nearly 13.8 billion years ago. As the universe expanded, this vast distance stretched the light emitted by the earliest stars and galaxies, making it faint and significantly redshifted. This redshift, a direct consequence of the universe's continuous expansion, stretches light to longer wavelengths, often pushing it beyond the visible spectrum into the infrared or even microwave ranges. This shift necessitates the use of highly sensitive instruments capable of detecting such faint and distant signals. Moreover, we encounter the cosmic microwave background, CMB, the afterglow of the Big Bang itself. The CMB is a crucial window into the early universe, offering a wealth of information, yet it also poses a significant challenge. This radiation forms a veil, beyond which traditional methods of observation are blind. Essentially, any light or electromagnetic radiation that predates the CMB, roughly 380,000 years after the Big Bang, remains obscured from our view, forever hidden in the depths of cosmic history. However, the challenges of peering into the universe's distant edges are not merely restricted to cosmic radiation. As technology progresses, we encounter inherent limits to the sensitivity and resolving power of our current instruments. Even with advanced space-based telescopes and ground observatories, capturing the light from these distant objects is only part of the equation. Interpreting it in the presence of the overwhelming cosmic background radiation proves to be just as difficult. Innovations like gravitational wave astronomy offer hope, though these new approaches will require breakthroughs, both technological and theoretical, to fully unlock the mysteries of the universe. Furthermore, the vast interstellar and intergalactic medium, the gas and dust between stars and galaxies, compounds the issue. This cosmic material absorbs, scatters, and reddens the light traveling through space, distorting the signals we receive. This distortion complicates the interpretation of data, requiring sophisticated models and advanced corrections to make sense of the faint, altered light. In addition to technological challenges, the theoretical framework we use to understand the universe itself is constantly tested at the edge of observable space. Our models, built on the principles of general relativity and quantum mechanics, are stretched to their limits in this extreme frontier. Any anomalies or unexpected findings in this region could force us to rethink established theories, potentially necessitating the development of new physics to explain the phenomena we encounter. And as we move forward, we delve deeper into one of the most captivating cosmic puzzles, dark matter. This invisible substance makes up roughly 27% of the universe, yet remains undetectable by traditional means. Unlike ordinary matter, which forms stars, planets, and everything visible to us, dark matter does not emit, absorb, or reflect light, making it nearly impossible to observe directly. However, its presence is inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The search for dark matter began in earnest in the 1930s, when astronomer Fritz Zwicky studied the Coma galaxy cluster. He found that the gravitational pull of the visible matter in the cluster was insufficient to account for the high velocities at which the galaxies within the cluster were moving. If only visible matter existed, these galaxies would have flown apart. This discrepancy led Zwicky to propose the existence of a vast amount of unseen matter, which he aptly named dark matter. Further evidence supporting the dark matter hypothesis came from Vera Rubin and her colleagues in the 1970s. Their observations of galaxy rotation curves revealed a puzzling anomaly. The stars within galaxies were moving much faster than predicted by the gravitational forces of the visible matter alone. Once again, this pointed to the existence of an invisible mass exerting the gravitational influence necessary to hold the galaxies together. Dark matter plays a critical role in the formation of cosmic structures, such as galaxies and galaxy clusters. Theories of cosmic evolution suggest that dark matter's gravitational pull helped to clump ordinary matter together, forming the dense regions that eventually evolved into the galaxies and clusters we see today. Without dark matter, the universe would have a vastly different structure, likely much simpler and possibly devoid of the conditions necessary for life. Yet, despite its crucial role, dark matter remains one of the greatest mysteries in science. It neither interacts with electromagnetic forces nor emits, absorbs, or reflects light, which makes it entirely invisible to conventional detection methods. However, its gravitational impact on visible matter provides indirect evidence of its presence. Several theoretical candidates for dark matter have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. Despite extensive efforts to detect these particles, none have yet been conclusively observed. The search for dark matter is not only a scientific pursuit to identify a mysterious form of matter, it is also a journey that challenges our very understanding of the universe. By uncovering the true nature of dark matter, scientists aim to deepen our comprehension of the fundamental forces that govern the cosmos. This quest bridges two seemingly disparate fields, cosmology and particle physics, revealing the intimate connection between the largest structures in the universe and the most minuscule particles that make up its unseen mass. Unraveling the mystery of dark matter offers more than just a solution to a cosmic riddle. It provides profound insights into the nature of space, time, and reality itself. As scientists continue to study the subtle fingerprints left by dark matter across the cosmos, the search for its true nature remains one of the most exciting and transformative journeys in modern science. And so the quest to understand the unseen forces shaping our universe began to evolve. The concept of dark matter was first introduced by the Swiss astronomer Fritz Zwicky in the early 20th century. Zwicky's observations of galaxy clusters revealed something extraordinary. He noticed that galaxies within these clusters were moving at speeds much higher than could be accounted for by the visible matter present. This discrepancy suggested the presence of an invisible mass that was not emitting any detectable light. Zwicky coined the term dunkle materie, or dark matter, to explain this unseen force, which would later become one of the most intriguing and elusive components of cosmology. In the 1970s, a new set of observations gave further credence to Zwicky's theory. Vera Rubin and her team conducted groundbreaking studies on the rotation curves of galaxies, the speeds at which stars orbit their galactic centers. According to Newton's law of gravitation, stars located at the outskirts of a galaxy should move more slowly than those closer to the center, where most of the mass is concentrated. But Rubin's measurements showed something unexpected. Stars at the outer edges of galaxies were moving at the same speed as those near the center. This anomaly could not be explained by visible matter alone, and it pointed to the existence of additional mass, likely dark matter, exerting its gravitational influence to stabilize the galaxies and prevent them from flying apart as they spun. The mystery of dark matter deepened with further investigations of the universe's early moments. The cosmic microwave background, CMB, radiation, a faint afterglow from the Big Bang, provided crucial evidence for the role dark matter played in shaping the universe. Satellites like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck Space Observatory made precise measurements of the CMB, detecting slight fluctuations in temperature that reflected density variations in the early universe. These density fluctuations, which match predictions made by models that include dark matter, revealed that this invisible force was pivotal in the formation of the universe's large-scale structure. Without dark matter, the cosmic structures we see today, galaxies, clusters, and the vast cosmic web, would not exist as they do. Moreover, gravitational lensing, an effect where the gravity of massive objects bends the light coming from more distant objects, further confirmed the presence of dark matter. Observations of light bending around galaxy clusters could not be fully explained by the visible matter alone. The bending of light indicated that invisible massive objects were present, their gravitational pull bending the light from distant galaxies. This phenomenon gave astronomers a unique way to detect and map dark matter's distribution across the universe. Together, these pieces of evidence, galaxy rotation curves, the cosmic microwave background, and gravitational lensing, paint a clear picture. Dark matter exists and plays a critical role in the universe. Its influence can be likened to an invisible scaffolding supporting the formation of galaxies and the structures we observe today. Dark matter's gravitational pull was crucial in the early stages of the universe, where it helped gas and dust coalesce into stars and galaxies. Without it, the universe's matter would have remained too diffuse to form the complex structures we see today. It's as if dark matter served as the cosmic architect, setting the stage for the creation of stars, galaxies, and the very fabric of the universe. At even larger scales, dark matter's influence shapes the cosmic web, a vast network of galaxies and galaxy clusters connected by filaments of dark matter and separated by cosmic voids. This web is the backbone of the universe, and dark matter's gravitational pull dictates the clustering and distribution of galaxies within it. Without dark matter, the web would not have its intricate structure, and the galaxies we observe today might never have formed into the clusters and filaments that define our universe's large-scale structure. Dark matter is not just the glue holding galaxies together, it's also the scaffolding that shapes the universe itself. One of the most fascinating aspects of dark matter is its role in gravitational lensing. This phenomenon occurs when the light from a distant object like a quasar or galaxy is bent by the gravitational pull of a massive foreground object. Dark matter's presence can be inferred from how it bends light, even though it cannot be directly seen. In this sense, dark matter acts as a cosmic lens, providing astronomers with a tool to map the unseen universe. It allows them to measure the distribution of dark matter and even track its movement across vast expanses of space, offering invaluable insight into its role in the cosmos. However, just as we began to uncover the secrets of dark matter, another mysterious force emerged: dark energy. The discovery of dark energy traces back to observations of distant supernovae in the late 1990s. Two independent teams of astronomers found that these supernovae were fainter than expected, suggesting they were farther away than previously thought. This unexpected faintness indicated that the expansion of the universe wasn't slowing down, as once believed. Instead, it was accelerating. Something was driving the acceleration, pushing galaxies apart at an ever-increasing rate. This mysterious force was dubbed dark energy. The nature of dark energy remains one of the most profound mysteries in modern physics. Unlike dark matter, which clusters and shapes galaxies, dark energy appears to be a uniform, pervasive force spread evenly throughout the universe. It has a repulsive property, pushing galaxies away from each other and accelerating the expansion of the cosmos. One leading theory suggests that dark energy could be a property of space itself, something inherent to the fabric of the universe, as described by Einstein's cosmological constant. This constant, initially introduced by Einstein in his equations of general relativity, was abandoned by him later as he considered it his biggest blunder. Yet in the face of dark energy, it has found new relevance. Another possibility is that dark energy is a dynamic field, similar to the electromagnetic fields we are familiar with, possessing a unique repulsive quality. This hypothetical field, sometimes called quintessence, might evolve over time, unlike the cosmological constant, which remains fixed. While dark matter's role in shaping the universe's structure is becoming clearer, the role of dark energy remains elusive, as it continues to accelerate the expansion of the universe at an ever-increasing pace, leaving scientists grappling with one of the most fundamental questions in cosmology. What is the true nature of dark energy, and how does it influence the future of our universe? As we continue to probe the depths of space, these cosmic mysteries, dark matter and dark energy, remain at the forefront of scientific inquiry, challenging our understanding of the universe and its origins. Together they form an invisible but integral part of the universe's grand design, holding the secrets to its past, present, and future. Theoretical models explore a variety of possibilities when it comes to the concept of quintessence, yet the elusive nature of this force still lacks concrete evidence. As we venture deeper into the enigmatic world of dark energy, we begin to unravel its extraordinary role in the cosmos, where it acts as a powerful agent of acceleration, driving the universe's expansion at an astonishing rate, far beyond what was initially anticipated. This mysterious force, which constitutes about 68% of the universe's energy content, operates as a kind of cosmic counterbalance to gravity. While gravity pulls matter together, dark energy pushes outward, causing the very fabric of the universe to stretch and accelerate, leading to the universe's rapid expansion. The discovery of this phenomenon has reshaped our understanding of the cosmos. Back in the late 1990s, astronomers embarked on studies of distant supernovae, expecting to find evidence that the universe's expansion was slowing down, a result of the gravitational forces pulling galaxies inward. But to their surprise, the data revealed an entirely different story. The universe was not slowing, but speeding up. This unexpected revelation directly pointed to the presence of dark energy, a force that was not just accelerating the expansion, but doing so at an increasing rate. Unlike matter, which clumps together to form galaxies and clusters, dark energy is thought to be uniformly distributed throughout space, creating a steady, repulsive force that accelerates the universe's expansion over time. The implications of this discovery stretch far beyond our immediate observations, shaping the very destiny of the universe. If dark energy remains constant, or even strengthens, the universe may continue to expand indefinitely, growing colder and more desolate as galaxies drift further apart and the formation of new stars ceases. In the most extreme models, dark energy's repulsive force could eventually reach a point where it causes a big rip, a cataclysmic scenario where the force becomes so overwhelming that it rips apart galaxies, stars, planets, and even atoms. Such possibilities challenge our most basic assumptions about the universe's future. To truly understand how dark energy affects cosmic expansion, it is not enough to simply measure how quickly the universe is stretching. We must look deeper at the very history of the universe itself. Thanks to the cosmic microwave background radiation, the faint afterglow of the Big Bang, and large-scale surveys of galaxies, scientists are able to piece together a timeline of cosmic evolution. These observations allow researchers to trace the influence of dark energy back through billions of years, unveiling how this enigmatic force has shaped the very structure of the cosmos. The study of dark energy remains one of the most compelling areas of modern cosmology. It challenges the very foundation of physics, pushing us to develop new theories that explain its behavior and impact. Quintessence, one such theory, proposes that dark energy is not a constant force, but rather a dynamic field that evolves over time with varying effects on the universe's expansion. This idea has far-reaching consequences for how we understand the forces that govern the cosmos. A common question often arises in the exploration of these cosmic phenomena. Are dark matter and dark energy the same thing, especially as we reach the outermost limits of the observable universe? Despite their similar names, dark matter and dark energy are distinct components, each playing a unique role in shaping the universe. Dark matter, which accounts for approximately 27% of the universe's energy content, acts as the cosmic glue, binding galaxies and galaxy clusters together. Without dark matter, the gravitational forces from visible matter would be insufficient to hold galaxies intact, particularly as they rotate at high speeds. Dark matter's influence is felt as strongly at the edges of the observable universe as it is within our local galactic neighborhood, helping to form the vast web-like structures of galaxies that populate the cosmos. In stark contrast, dark energy is the repulsive force that drives the accelerated expansion of the universe. Unlike dark matter, it does not clump or concentrate, but is evenly distributed across space, providing a force that counteracts gravity's pull and pushes galaxies apart. As we look further into the cosmos, we can observe the increasing rate of the universe's expansion, a direct consequence of dark energy's influence. The further we peer into space, the faster galaxies seem to be moving away from us, a phenomenon that underscores the pervasive presence of dark energy throughout the cosmos. The distinction between dark matter and dark energy is evident across the universe, from our local galactic neighborhood to the farthest reaches of space. Though both forces are crucial to the structure and evolution of the universe, they operate in fundamentally different ways. Dark matter attracts, pulling cosmic structures together, while dark energy repels, accelerating the universe's expansion. This duality is central to our understanding of cosmic evolution, impacting everything from the formation of galaxies to the ultimate fate of the universe. As we explore the outer limits of the universe, we are confronted with the limits of our current knowledge. Here at the edges of observable space, dark matter and dark energy leave an indelible mark on the cosmic landscape, shaping it in profound and distinct ways. The ongoing study of these mysterious forces challenges our theories of physics, prompting us to revise our understanding of the universe. As our observational capabilities continue to evolve, we may uncover new insights into how dark matter and dark energy operate, though their fundamental differences are likely to remain a cornerstone of our current cosmological models. Continuing our journey into the boundless expanse of the cosmos, we delve deeper into the vast ocean of human imagination, where ideas about the universe swirl like stars in the night sky. This chapter invites you to explore the rich and thought-provoking theories that challenge and expand our understanding of the cosmos, guiding us through the unknown, where the familiar meets the mysterious. At the forefront of this intellectual voyage lies the captivating idea of the multiverse, a theory so profound it stretches the limits of our comprehension. Imagine, if you will, that our universe, with all its galaxies, stars, and endless mysteries, may not be the only one. According to the multiverse theory, we are but a single bubble in an infinite cosmic foam, surrounded by an untold number of other universes, each with its own unique laws of physics, history, and perhaps even versions of reality beyond our wildest imagination. The multiverse hypothesis, though seemingly outlandish, emerges from the intersection of some of the most groundbreaking theories in cosmology, including inflationary theory, string theory, and quantum mechanics. It suggests a cosmos far more complex and expansive than we could have ever envisioned. The idea stems from the inflationary theory, which proposes that in the moments following the Big Bang, the universe expanded at an extraordinary rate, leading to the formation of separate pockets of space-time. These pockets could have evolved into individual universes within a larger multiverse. String theory, too, adds fuel to this theory. In its search for a unified framework that connects the quantum and relativistic worlds, it introduces the notion of extra dimensions, dimensions that, in different configurations, could give rise to entire universes, each one potentially governed by a distinct set of physical laws. Quantum mechanics, with its principle of quantum decoherence, takes this even further, suggesting that every quantum possibility results in its own parallel universe, where every conceivable outcome is played out in its own reality. Yet despite the allure of these theories, the multiverse remains speculative, its existence still unproven. The very nature of the theory presents a formidable challenge. How can we observe or interact with universes beyond our own, particularly when they exist outside the observable limits of light and time? The very tools we rely on to understand the cosmos, our telescopes and scientific instruments, are rendered powerless by the vast distances and barriers imposed by these parallel universes. Undeterred, physicists and cosmologists press on, analyzing cosmic microwave background radiation and scrutinizing other cosmic phenomena for clues that might hint at the existence of the multiverse. With each discovery, they inch closer to unlocking the secrets of this uncharted frontier, daring to test the very boundaries of what can be known and understood about our universe and its possible siblings. Moving beyond the multiverse, we encounter another thrilling possibility at the cutting edge of theoretical physics, the existence of wormholes. These enigmatic structures, often depicted in science fiction as shortcuts through space-time, could offer a means of traversing vast distances across the universe, or even between different universes altogether. Rooted in the equations of general relativity, wormholes represent a real, albeit highly speculative, phenomenon, an exotic pathway that could connect distant parts of the cosmos. The theory behind wormholes is grounded in the work of Albert Einstein and Nathan Rosen, who proposed the concept of an Einstein-Rosen bridge in the 1930s. This theoretical structure, resembling a tunnel through spacetime, could potentially serve as a bridge between two separate regions of spacetime, allowing for instant travel across vast distances. In theory, a wormhole could even connect our universe to another, offering tantalizing possibilities for exploration beyond our own cosmic boundaries. However, the concept of wormholes is far from simple. For a wormhole to be traversable, it would require exotic matter, substances with negative energy density, that could keep it open and prevent its collapse under the immense gravitational forces at play. The challenge, of course, lies in the fact that such exotic matter has never been observed in nature, and its creation remains purely hypothetical. Without this crucial ingredient, the idea of traversable wormholes remains an intellectual curiosity, one that challenges our understanding of both the universe and the limits of human ingenuity. Nevertheless, the search for evidence of wormholes continues, driven by the hope that advanced astronomical tools might one day reveal signs of their existence. One possibility is that the gravitational effects of a wormhole might influence the path of light, creating a distortion similar to a gravitational lens. If such a phenomenon were detected, it could provide the first indirect evidence of wormholes' existence, offering new clues in the ongoing quest to understand the fundamental nature of time itself. Despite the theoretical potential, the practical reality of wormholes and their role in space travel or communication remains far beyond our current technological capabilities. The energy required to manipulate space-time on such a scale and the challenges of stabilizing a wormhole long enough for human use are daunting. Still, the mere existence of these ideas offers a glimpse into the vastness of possibility, fueling the imaginations of scientists and dreamers alike. As we continue our journey through the realm of theoretical physics, we encounter yet another awe-inspiring idea: the theory of everything. This ambitious framework seeks to unify the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single cohesive theory. It is the holy grail of modern physics, the dream of every physicist who has ever sought to understand the deepest workings of the universe. The theory of everything aims to bridge the gap between two pillars of modern physics: general relativity and quantum mechanics. General relativity, Einstein's groundbreaking theory, describes gravity as the curvature of spacetime caused by mass and energy. It has been validated by countless experiments and observations, from the bending of light around galaxies to the behavior of black holes. Quantum mechanics, on the other hand, governs the behavior of particles at the smallest scales, explaining phenomena like the uncertainty principle and quantum entanglement. Although both theories have been incredibly successful in their respective domains, they are fundamentally incompatible. The search for a theory of everything is an ongoing effort to reconcile these two seemingly disparate worlds into one unified framework. In this endeavor, scientists are exploring a variety of approaches, from string theory to loop quantum gravity, hoping to find a path that will ultimately lead to the ultimate understanding of the universe's most fundamental laws. The pursuit of such a theory represents not just the peak of intellectual achievement, but the very essence of human curiosity, our unyielding desire to know the universe and our place within it. In the quest to understand the universe's deepest secrets, two foundational theories in modern physics seem to contradict each other, yet they are both irreplaceable in shaping our understanding: general relativity and quantum mechanics. General relativity, formulated by Einstein, tells us that the fabric of space-time is smooth, curved by the presence of mass and energy. On the other hand, quantum mechanics paints a different picture at the smallest scales, suggesting that space-time is turbulent, frothy, and filled with quantum fluctuations. These two pillars of physics have stood the test of time, yet their incompatibility presents one of the greatest challenges in theoretical physics. The theory of everything seeks to bridge this divide, aiming to combine these seemingly incompatible realms into a single unified framework. One of the most prominent candidates in this grand search is string theory. This theory proposes that the fundamental building blocks of the universe are not point-like particles, but instead one-dimensional strings vibrating at different frequencies. The vibration of these strings dictates the properties of particles, such as their mass and charge. What makes string theory so compelling is its potential to integrate quantum mechanics with gravity, two forces traditionally viewed as separate entities. By proposing that the fundamental forces of nature can be unified under a common principle, string theory holds the tantalizing possibility of explaining all of reality under one set of rules. However, another intriguing approach to unifying quantum mechanics and general relativity is loop quantum gravity, LQG. Unlike string theory, LQG does not introduce extra dimensions or require the existence of strings. Instead, it focuses on quantizing spacetime itself. LQG treats spacetime as a collection of tiny loops woven together into a fabric, attempting to explain gravity at the quantum level without violating the principles of quantum mechanics. This theory aims to provide a quantum theory of gravity, offering a new lens through which we might view the fabric of the cosmos. But what does quantum mechanics have to do with the vastness of the cosmos? It may seem that these two realms, quantum mechanics, which deals with the tiny world of atoms and subatomic particles, and the cosmos, which spans across vast distances, are worlds apart. Yet, quantum mechanics plays an integral role in shaping the universe at every scale, influencing everything from the birth of stars to the structure of galaxies. One of the most profound quantum phenomena that governs the universe is quantum tunneling, which allows particles to pass through energy barriers they would otherwise be unable to overcome. This process is responsible for the nuclear fusion that powers stars, including our very own sun. Without quantum tunneling, stars wouldn't ignite, and life as we know it wouldn't exist. Quantum mechanics also governs the earliest moments of the universe's existence. Immediately after the Big Bang, the cosmos was a hot, dense soup of particles. In this primordial state, tiny quantum fluctuations, minute variations in energy, occurred. These fluctuations were stretched by cosmic inflation, a period of rapid expansion in the universe's early history, into the seeds for the large-scale structures we see today: galaxies, galaxy clusters, and the cosmic web. The distribution of matter in the universe, from the cosmic microwave background radiation to the arrangement of galaxies, bears the imprint of these early quantum fluctuations. The mysteries of quantum mechanics are not confined to the birth and evolution of the universe. Quantum effects are also key to understanding the most enigmatic objects in the cosmos: black holes. At the heart of a black hole, gravity is so intense that not even light can escape. Yet, quantum mechanics suggests that black holes are not completely devoid of energy. Through the work of physicist Stephen Hawking, we learned that black holes can emit radiation, a phenomenon now known as Hawking radiation. This discovery brought quantum mechanics into the realm of general relativity, offering insights into the behavior of black holes and providing a tantalizing glimpse into how these two theories might one day be reconciled. Yet the mysteries don't end there. One of the most intriguing phenomena in the cosmos is dark matter, a form of matter that exerts gravitational forces but doesn't emit light. While we cannot directly observe dark matter, its presence is inferred from its gravitational effects on galaxies and galaxy clusters. Quantum mechanics might hold the key to understanding this elusive substance. Theoretical particles like WIMPs, weakly interacting massive particles, or axions, like proposed by quantum theories extending the standard model of particle physics, could be the building blocks of dark matter. Understanding how these hypothetical particles interact with gravity and quantum fields could unlock new insights into the very fabric of the universe. As we continue to explore the relationship between quantum mechanics and the cosmos, one question remains: is time travel theoretically possible? While it may seem like science fiction, time travel is a topic that has been seriously considered by physicists, especially within the framework of general relativity. According to Einstein's theory, spacetime is curved by mass and energy, and this curvature can, in theory, lead to closed time-like curves, loops in spacetime that would allow an object to return to its past. These solutions to the equations of general relativity suggest that time travel is not only theoretically possible, but may be a natural consequence of the structure of spacetime itself, One potential means of achieving time travel is through wormholes, hypothetical tunnels in spacetime that could connect distant points in space and time. If wormholes could be stabilized with exotic matter, which possesses negative energy density, it might be possible to traverse them and travel through time. However, the existence of stable wormholes remains speculative, and the practical challenges of creating one are immense. Similarly, the concept of cosmic strings, hypothetical defects in space-time left over from the early universe, has also been proposed as a means of time travel. If two cosmic strings were to pass close to each other, or if a single string moved at relativistic speeds, it might create the conditions necessary for time travel. But again, these ideas remain theoretical, and many hurdles stand in the way of turning them into reality. Even though the concept of time travel tantalizes our imagination, it also raises profound scientific and philosophical questions. The famous grandfather paradox, where a time traveler could prevent their own existence by altering events in the past, challenges our understanding of causality and the nature of time itself. Moreover, the energy required to manipulate space-time in such a way as to achieve time travel is currently far beyond our technological capabilities. In addition to these theoretical questions, quantum mechanics itself offers fascinating possibilities for time travel, particularly through the phenomenon of quantum entanglement. In this strange effect, two particles can become so deeply linked that the state of one instantly affects the state of the other, no matter the distance between them. Some interpretations of quantum mechanics suggest that entangled particles might be connected by wormholes, further linking quantum phenomena to the fabric of spacetime. While time travel based on quantum entanglement remains speculative, it suggests that the nature of time and space is far more complex than we currently understand. Now we come to one of the most profound and existential questions in science. Could life exist elsewhere in the universe? With billions of stars and even more planets scattered across the cosmos, it seems likely that we are not alone. The discovery of thousands of exoplanets by the Kepler Space Telescope has revealed a wealth of potentially habitable worlds where conditions might be right for liquid water, the key ingredient for life as we know it. These planets, orbiting distant stars, may offer the right conditions for life to flourish. The search for extraterrestrial life extends beyond exoplanets to the moons of our own solar system. Mars, once home to flowing water, and moons like Europa and Enceladus with their subsurface oceans, have become prime missions searching for microbial life. On these worlds, life could exist in forms vastly different from what we are familiar with. Scientists have even speculated about the possibility of life based on silicon instead of carbon, or life that exists in environments that would be hostile to Earth-based organisms. The search for life raises another fascinating question. What would life elsewhere look like? While carbon-based life forms are all we know, the universe may harbor life with entirely different biochemistries. Life forms could thrive in environments that are radically different from Earth's, such as in the thick atmospheres of gas giants or in the frigid oceans beneath the ice crusts of distant moons. The possibility of discovering alien life not only deepens our understanding of biology, but also challenges our very definitions of life itself. As we gaze out into the stars, these questions about time, space, the nature of the cosmos, and the potential for life beyond Earth remain as pressing and as mysterious as ever. Continuing our journey into the vast and uncharted realms of space, we find ourselves on the brink of discovery, gazing deeper than ever before into the mysteries of the universe. The instruments that make this exploration possible are nothing short of remarkable. Telescopes. These wondrous creations of science and engineering serve as our eyes into the cosmos, enabling us to witness phenomena from our neighboring planets to galaxies that lie billions of light years away. These powerful devices gather and focus light, allowing us to observe celestial objects that would otherwise remain hidden in the inky blackness of space. The larger a telescope's light collecting area, the fainter the objects it can detect, revealing more intricate details of the universe's vastness. There are two major types of telescopes that we rely on, refracting and reflecting. Each employs distinct mechanisms to capture and focus light, and each has shaped our understanding of the universe in unique ways. Refracting telescopes, the first to be invented, utilize lenses to focus light. The primary lens bends incoming light rays, focusing them on a single point, where the image is magnified and viewed through an eyepiece. These telescopes were revolutionary in their time, with the legendary Galileo Galilei using them in the early 1600s to make groundbreaking discoveries about our solar system. Reflecting telescopes, on the other hand, use mirrors instead of lenses. A large curved mirror collects light and reflects it to a focal point, while a secondary mirror may direct the light toward an eyepiece or a camera. Reflectors have significant advantages, including their ability to avoid chromatic aberration, a common distortion seen in refracting telescopes, and their capacity to build much larger telescopes. This is because mirrors can be supported from behind, minimizing sagging and distortion. As technology advanced, so too did our ability to explore the universe through different wavelengths of light. Beyond the traditional optical telescopes, we now have specialized instruments designed to observe non-visible forms of electromagnetic radiation, including radio, infrared, ultraviolet, X-rays, and gamma rays. These telescopes provide invaluable insights into parts of the universe that optical telescopes cannot reach. For example, radio telescopes use massive dish antennas to detect radio waves emitted by celestial objects, revealing hidden wonders like pulsars, quasars, and even the remnants of the Big Bang itself, cosmic microwave background radiation. Space-based telescopes, such as the iconic Hubble Space Telescope, operate above Earth's atmosphere, which would otherwise block or distort many wavelengths of light. With this vantage point, they offer a clearer and more comprehensive view of the universe, observing the cosmos in optical, ultraviolet, and near-infrared light. The images captured by these instruments are not just photographs, they undergo sophisticated processing and analysis. Using advanced algorithms, astronomers can reveal fine details that would be invisible in raw data. These analyses help us measure the distance, composition, temperature, and even the movement of distant stars, planets, and galaxies, contributing to our ever-growing understanding of the universe's structure and the laws that govern it. But among all the advancements in telescope technology, perhaps the most profound leap in our journey into space is the advent of the James Webb Space Telescope, JWST. Launched in late 2021, the JWST represents the zenith of space-based telescope technology. Designed to observe the universe primarily in the infrared spectrum, it is far more powerful than any telescope that came before it. With its ability to peer through dense cosmic dust clouds, the JWST can observe distant stars and galaxies that have long been hidden from view. Its massive 6.5-meter primary mirror provides a light-gathering capacity over 6 times greater than that of the Hubble Space Telescope, enabling it to see objects farther away and thus further back in time than ever before. One of the JWST's primary goals is to probe the edge of the observable universe, aiming to uncover the earliest galaxies formed after the Big Bang, over 13.5 billion years ago. By studying these primordial galaxies, astronomers hope to unlock the secrets of the universe's infancy, shedding light on the processes that led to the formation of the cosmic structures we see today. The JWST's infrared capabilities are crucial for this mission, as the expansion of the universe has stretched the light from these ancient galaxies into the infrared range, a phenomenon known as redshift. The JWST is also set to revolutionize our understanding of exoplanets. With its advanced instruments, it will study the atmospheres of these distant worlds, searching for potential signs of life. By detecting key molecules such as water vapor, carbon dioxide, and methane, it could offer the first hints of biological processes occurring light years away. Moreover, the JWST is designed to investigate the formation of stars and planetary systems within our own galaxy, providing unparalleled insights into the processes that gave birth to our own solar system and the vast variety of planetary systems scattered across the Milky Way. In conclusion, the James Webb Space Telescope marks a monumental step in humanity's quest to understand the cosmos. Its advanced technology, unique capabilities, and bold scientific objectives make it an essential tool for exploring the unknowns of the universe. From uncovering the origins of galaxies to detecting signs of life beyond Earth, the JWST promises to reveal answers to some of the most profound questions humanity has ever asked. As we continue to look toward the stars, it is clear that our journey has only just begun, and the JWST is leading the way to a future full of discovery and wonder. By studying these early galaxies, astronomers seek to unlock the mysteries of the universe's formative years, exploring the creation of the first cosmic structures. This endeavor is pivotal to understanding how the intricate cosmic web of galaxies we observe today came into being. Through detailed observations of these distant galaxies, scientists aim to gain profound insights into the processes that shape the universe, expanding our knowledge of its complex evolution. The James Webb Space Telescope, JWST, is at the forefront of this exploration, and its unparalleled infrared capabilities are crucial for these investigations. As the light from these faraway galaxies travels to us, it undergoes a stretching effect known as redshift, where the wavelengths of light shift into the infrared range due to the continuous expansion of the universe. Only with JWST's advanced instruments can we peer deeply into this cosmic past. But the mission of the JWST doesn't stop there. It will also turn its gaze toward exoplanets orbiting distant stars, with the goal of identifying signs that might indicate habitability or even the presence of life. The JWST's powerful spectrometers can analyze the chemical makeup of these exoplanet atmospheres, detecting crucial molecules like water vapor, carbon dioxide, and methane. These molecules are essential markers of biological processes, making the search for life outside our planet one of the most exciting aspects of this mission. The ability to discern such features on exoplanets will bring us closer than ever to answering the age-old question, are we alone in the universe? Additionally, the JWST is set to revolutionize our understanding of star and planet formation within our very own galaxy. The telescope will focus on molecular clouds, the dense, cold regions where new stars are born, and will provide groundbreaking insights into the conditions that foster the birth of stars and planetary systems. These observations will be invaluable not only in unraveling the origins of our solar system, but also in shedding light on the vast diversity of planetary systems that populate the Milky Way. Through its study of these primordial nurseries of stars, the JWST promises to expand our knowledge of how planetary systems evolve, both within our galaxy and beyond. As the JWST embarks on its mission, its observations will undoubtedly transform our understanding of the universe. Its powerful instruments are expected to challenge existing theories, uncover previously hidden phenomena, and answer some of the most fundamental questions in cosmology. From capturing the faintest glimmers of light from the earliest galaxies formed after the Big Bang, to uncovering the intricate processes that shape the stars and planets around us, the JWST will provide an unprecedented window into the history and evolution of the cosmos. This journey through time will bring us closer than ever to comprehending the universe's vast scale and, perhaps more importantly, our place within it. Over the past few decades, satellites have revolutionized astronomy by offering a vantage point beyond the Earth's atmosphere, free from the distortions caused by the planet's air. This breakthrough has opened up entirely new dimensions for exploration, allowing scientists to peer deeper into the universe than ever before. From the cosmic microwave background radiation to the discovery of exoplanets, satellites have provided invaluable tools for mapping the universe, each contributing unique perspectives that have dramatically advanced our cosmic knowledge. The launch of the Hubble Space Telescope in 1990 marked a pivotal moment in space exploration. Orbiting far above Earth, free from atmospheric interference, Hubble captured images of remarkable clarity, unveiling the intricate and dynamic structure of the universe. The Hubble Space Telescope's discoveries have reshaped our understanding of the cosmos. Hubble's observations have led to significant breakthroughs, including the revelation of the age of the universe, the discovery of dark energy, and the study of black holes. Through its stunning deep-field images, Hubble has granted us a glimpse into the universe's early stages, revealing galaxies billions of light years away and showing us how galaxies evolve over cosmic time. These images have not only expanded our knowledge of the universe's history, but also challenged our understanding of its future. Another game-changing satellite, the Cosmic Background Explorer, SOBE, launched in 1989, played a crucial role in supporting the Big Bang theory. By mapping the cosmic microwave background radiation, the afterglow of the Big Bang, COBE provided key evidence for the universe's early moments. Its measurements confirmed that the universe's background radiation is remarkably uniform, with slight variations that support the idea of cosmic inflation. These findings were pivotal, earning the Nobel Prize in Physics in 2006. Following COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite refined these measurements, offering a more precise map of the cosmic microwave background. These observations helped establish critical parameters about the universe's age, composition, and expansion rate, refining our understanding of cosmology and our place in it. Satellites have also played a central role in the search for exoplanets. The Kepler Space Telescope, launched in 2009, was dedicated to finding Earth-sized planets in the habitable zone of their stars, where liquid water could exist. Kepler's discoveries have transformed our view of the galaxy, revealing that exoplanets are far more common than previously thought. Thousands of these planets have been identified, challenging our ideas about planet formation and potentially offering a glimpse into worlds that could host life. Meanwhile, satellites like the Solar Dynamics Observatory, SDO, have contributed greatly to our understanding of the sun and its influence on space weather. Through observations of solar flares, sunspots, and coronal mass ejections, these satellites have provided crucial data on the sun's activity and its effects on Earth's environment. Understanding solar phenomena is vital not only for space exploration, but also for safeguarding modern technology that relies on satellite communications and navigation systems. How do scientists use data from telescopes to study distant celestial objects? Light from these objects, whether emitted, absorbed, or reflected, travels vast distances to reach us. Telescopes, whether space-based or ground-based, collect this light and focus it into instruments that analyze its composition. Spectroscopy is one of the primary techniques used to study the light from distant objects. By analyzing the spectrum of light, scientists can identify the unique fingerprints of chemical elements, revealing the composition of stars, galaxies, and nebulae. This process also allows astronomers to measure the temperature, density, and motion of these objects, whether they are moving toward or away from us, as indicated by redshift or blue shift in their spectral lines. Photometry is another essential technique which involves measuring the intensity of light over time. By tracking how the brightness of an object changes, astronomers can infer its size, luminosity, distance, and even detect planets passing in front of stars. Variations in brightness can also reveal dynamic processes, such as the pulsation of stars or the interaction between binary stars. The data collected from these observations is often processed using sophisticated algorithms and computational models, which correct for distortions caused by the Earth's atmosphere and other sources of interference. Advances in digital imaging and computing power have greatly improved the volume and quality of data, enabling discoveries that were once unimaginable. In addition, the technique of parallax is used to measure the distance to nearby stars. By observing a star's position from different points in Earth's orbit, astronomers can calculate its distance based on the apparent shift in position. This method, although primarily useful for nearby stars, has been instrumental in refining our measurements of stellar distances and further enhancing our understanding of the universe's vast scale. Through these groundbreaking methods, scientists continue to push the boundaries of our knowledge, bringing us ever closer to comprehending the mysteries of the universe. As we look to the stars, the shifting positions of distant celestial bodies offer scientists a unique opportunity to measure their distance from Earth. This is accomplished by observing the subtle movements of stars against the backdrop of more distant stationary stars. By tracking how a star's position changes as Earth orbits the Sun, astronomers can precisely calculate its distance. This crucial measurement serves as a foundation for building what is known as the cosmic distance ladder, a method that allows us to measure the distances of even more remote objects, such as galaxies far beyond our reach. However, as we aim our most powerful telescopes toward the farthest corners of the universe, astronomers are met with significant hurdles. These challenges are compounded by the immense distances involved, the faintness of the objects they seek to observe, and the inherent limitations of current technology. Yet, overcoming these challenges is vital if we hope to expand our understanding of the universe's vast structure, evolution, and the forces that govern it. One of the most formidable obstacles astronomers face is the sheer distance to distant galaxies, which often lie millions, if not billions of light years away. The farther away an object is, the fainter its light becomes, which makes it incredibly difficult to detect and study. To make matters even more complex, the universe is constantly expanding. This expansion causes the light emitted by distant galaxies to stretch into longer, redder wavelengths, a phenomenon known as redshift. As a result, much of the light emitted by these galaxies falls outside the visible spectrum, requiring astronomers to use specialized instruments like infrared and radio telescopes to observe them. For ground-based telescopes, another challenge arises from atmospheric interference. The Earth's atmosphere distorts and absorbs the light coming from distant objects, which not only blurs our view, but also limits the amount of information we can gather. Space telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, circumvent this problem by operating above Earth's atmosphere. However, these space-based observatories come with their own set of issues, namely their complexity and high cost, limiting the number of missions that can be launched. The finite speed of light itself also places a fundamental limitation on our ability to observe the universe in real time. When we observe distant galaxies, we're essentially looking into the past, sometimes billions of years into the past. This means we're unable to learn about the current state of these distant objects, which complicates our understanding of cosmic evolution. In addition to these challenges, the vast amount of data generated by modern telescopes presents another significant hurdle. Telescopes today collect enormous quantities of data that require advanced computational techniques and sophisticated software to process and analyze, extracting meaningful insights from this data, such as the distribution of dark matter, the properties of galaxies, or the rate of cosmic expansion, requires powerful algorithms and immense computational resources. Another obstacle comes from interference caused by objects in our own galaxy. Light from nearby stars, as well as dust and gas within our Milky Way, can obscure our view of more distant galaxies, making it even more difficult to isolate the faint light from the distant objects we're studying. To counteract this, astronomers have developed specialized techniques to filter out this foreground noise and focus on the light coming from the target galaxies themselves. Despite these challenges, the field of astronomy is rapidly advancing. Technological innovations, such as more sensitive detectors and the launch of new telescopes capable of observing different wavelengths of light, are enabling astronomers to overcome some of these barriers. These efforts are peeling back the layers of the universe, revealing the intricate dance of galaxies across time and space. With each new breakthrough, we come closer to understanding the vast cosmos in all its glory. Now, let us turn the page and journey back to the very beginning, back to the moment that marked the birth of everything we know, the Big Bang. This catastrophic event, which occurred around 13.8 billion years ago, set the stage for the universe as we know it today. Contrary to what the name might suggest, the Big Bang was not an explosion in space. Instead, it was the rapid expansion of space itself, from an infinitely dense and hot state to the vast, cooler cosmos we now inhabit. From this singular event, all space, time, matter, and energy emerged, setting in motion the formation of galaxies, stars, planets, and eventually life. The Big Bang Theory stands as the most widely accepted explanation for the origin of the universe, supported by a multitude of evidence from various scientific fields. One of the most compelling pieces of evidence comes in the form of the cosmic microwave background, CMB radiation, a faint afterglow that permeates the entire universe. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, this radiation provides a snapshot of the universe as it existed roughly 380,000 years after the Big Bang, when the cosmos cooled enough for photons to travel freely through space. The uniformity and slight fluctuations in the CMB radiation align with the predictions made by the Big Bang Theory, offering a direct glimpse into the early universe. In addition to the CMB, the observation of the universe's expansion is another pillar supporting the Big Bang Theory. In the 1920s, Edwin Hubble's observations revealed that galaxies are moving away from one another, indicating that the universe itself is expanding. When traced backward in time, this expansion implies that the universe must have originated from a single, incredibly dense point. Hubble's law, which states that the farther a galaxy is from us, the faster it is receding, has been confirmed by subsequent observations, further solidifying the Big Bang theory as the leading explanation for the universe's origins. Moreover, the theory accounts for the abundance of light elements like hydrogen, helium, and lithium. In the first few minutes after the Big Bang, nuclear reactions took place that produced these elements in the exact proportions observed in the universe today. This process, known as nucleosynthesis, is another strong piece of evidence for the Big Bang theory, cementing its place as the cornerstone of modern cosmology. Despite its success in explaining many aspects of the universe's origin, the Big Bang theory also raises new questions and mysteries. For example, it cannot explain the nature of dark matter and dark energy, which are believed to make up most of the universe's mass energy content. Furthermore, the theory offers no explanation for what happened before the Big Bang or what triggered it, leaving room for further research and discovery. These gaps in our understanding suggest that while the Big Bang theory has been immensely successful, it is far from the final word in our quest to understand the cosmos. As we continue to explore, new discoveries may reveal even deeper layers of the universe's enigmatic past. From the cataclysmic birth of the universe in the Big Bang, a singular moment of unimaginable power, the cosmos embarked on an extraordinary journey, unfolding across vast stretches of time. What began as a scorching, dense expanse has now blossomed into the intricate, vast universe we observe today, filled with galaxies, stars, and planets. Yet, the story of this evolution is far more than a simple tale of expansion. It is the narrative of cosmic cooling, gravity's tireless dance, and the relentless shaping of the universe over billions of years, from its fiery birth to its current form. In the moments following the Big Bang, the universe was an unrecognizable maelstrom, a boiling cauldron of particles and radiation. The heat and density were so intense that atoms couldn't form, and the universe was a sea of energetic chaos. This early era, known as the Planck epoch, was defined by the unification of the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces, all operating as a single entity. As the universe expanded, this scorching environment cooled rapidly, and the forces began to decouple. From this cooling, the first subatomic particles, protons, neutrons, and electrons emerged, marking the very first stages of structure in the universe. Roughly 380,000 years after the Big Bang, the universe had cooled enough for the formation of neutral hydrogen atoms through a process called recombination. This critical moment transformed the universe from an opaque, glowing plasma into a transparent space. Photons, light particles, could finally travel freely, creating the cosmic microwave background radiation, an ancient snapshot of the infant universe that scientists continue to study today. For the following hundreds of millions of years, the universe entered a dark age, an era devoid of light, as stars had yet to ignite. But gravity, the quiet architect of the cosmos, began to pull together clouds of gas and dark matter, forming the seeds of future galaxies. The end of the cosmic dark ages came when the first stars began to shine, born from the gravitational collapse of these primordial gas clouds. These stars were massive and short-lived, burning brightly before exploding in spectacular supernovae. These violent deaths scattered heavy elements across the cosmos, elements like carbon, oxygen, and iron, precursors to the very building blocks of life. In these ancient starry nurseries, galaxies began to take shape, born from the collapse of dark matter halos that gathered gas and dust. Inside these galaxies, new stars formed, surrounded by disks of material that eventually coalesced into planets, asteroids, and comets. Over time, galaxies grew in size and complexity, merging with each other in grand cosmic collisions that sculpted the variety of galactic shapes, spirals, ellipticals, and irregular forms, visible to us today. As the universe continued its expansion, the rate of star formation gradually slowed. The cosmos had entered a more stable phase, where the death of old stars balanced the birth of new ones. Yet, a new discovery shifted our understanding of the universe's future: the enigmatic presence of dark energy. This mysterious force, unseen yet pervasive, is causing the accelerated expansion of the universe. The very fabric of space-time itself is stretching, driving galaxies apart and causing them to drift further into isolation. What does this mean for the universe's ultimate fate? Today, the universe is a sprawling, intricate web of galaxies, each a vast island in an ever-expanding ocean of space. These galaxies, connected by long strands of dark matter, stretch across the cosmos, forming a network that resembles a cosmic web. This structure, from the tiniest planetary systems to the largest galactic clusters, is the result of nearly 14 billion years of cosmic evolution, driven by the fundamental forces of physics. The universe we see today is a grand tapestry, woven together over eons, a dynamic interplay of forces that turned a singularity into the complex and ever-expanding cosmos we explore. However, the universe's future is far from certain. The fate of the cosmos hinges on the properties of dark energy, which, if it continues to dominate the cosmic stage, will push galaxies further apart. In such a scenario, distant galaxies will speed away, disappearing beyond our reach and beyond the cosmic horizon. The universe, once full of stars and galaxies, would become increasingly cold and empty, heading toward a state called the Big Freeze, or heat death. In this future, the universe would reach a point of maximum entropy, where no meaningful exchanges of energy occur, signaling the end of all astronomical processes, and perhaps the universe itself. Another, though less likely, outcome is the Big Crunch, a scenario where the expansion of the universe reverses. If dark energy were to weaken, or if there were enough matter in the universe to gravitationally pull everything back together, the universe might collapse in on itself, returning to a singularity. This collapse could trigger another Big Bang, creating a cyclical model of cosmic rebirth. However, the overwhelming evidence supporting the accelerated expansion of the universe suggests that the Big Crunch is an unlikely fate. A more speculative yet fascinating possibility is the Big Rip. In this scenario, the dark energy that is currently accelerating the expansion of the universe would intensify over time, eventually becoming so strong that it would tear apart galaxies, stars, planets, and even atoms. The very fabric of the universe would unravel, leaving no structure behind, a chaotic, disintegrating cosmos. Alongside these dramatic possibilities for the universe's end, the future of stars, galaxies, and black holes looms large in the cosmic timeline. Stars will continue to form for trillions of years as gas within galaxies is used up. Eventually, however, star formation will cease. The remaining stars will burn out, leaving behind remnants: white dwarfs, neutron stars, and black holes. Over an unimaginable span of time, black holes themselves may eventually evaporate through a process called Hawking radiation, leaving the universe even more barren than before. Yet, even as the universe moves toward these distant futures, one thing is certain: the cosmic journey from the fiery moments of the Big Bang to the present and beyond is a story of endless change, of birth, death, and rebirth. The universe will continue to evolve, driven by the fundamental forces that have shaped it from the beginning. Galaxies will evolve in remarkable and complex ways, their fates intertwined by the gravitational forces that shape the cosmos. They will merge and cannibalize smaller galaxies, and their stellar populations will age, eventually giving way to the slow fade of cosmic light. Over the course of trillions of years, even black holes, those mysterious behemoths at the heart of galaxies, are expected to evaporate through the process of Hawking radiation. As they shrink and disappear, they will leave behind a universe filled with low-energy photons and subatomic particles, barely whispering the remnants of the once vibrant stars. These projections, visions of the universe's distant future, come from the best models and theories we currently have. But as our understanding of dark energy, dark matter, and the very fabric of the universe deepens, so too will our predictions. Cosmology is an ever-evolving field where each breakthrough offers a new lens through which we can view the cosmos, reshaping our understanding of the past, present, and future. Turning our attention to the Milky Way, we see that even the most majestic galaxies are not immune to the forces of time and change. Our home galaxy, teeming with stars, planets, and nebulae, is on a fascinating and inevitable collision course with the Andromeda Galaxy, our nearest galactic neighbor. This event, predicted by astronomical observations and simulations, is set to occur in about 4 billion years. Though a galactic merger may sound like the stuff of science fiction, complete with cataclysmic star crashes, this event will unfold slowly over hundreds of millions of years. The vast distances between stars make direct collisions between them unlikely. Instead, the galaxies will be sculpted by each other's gravitational forces, eventually giving birth to a new, larger elliptical galaxy, a creation sometimes called Milkomeda or Milkdromeda. As these two galaxies begin to merge, the interaction of gas and dust clouds will ignite a spectacular surge of star formation. New stellar clusters will emerge, some regions becoming denser while others are stripped away, contributing to the formation of tidal tails, elongated streams of stars and gas drawn out by the cosmic dance. Meanwhile, the supermassive black holes at the centers of both galaxies will spiral toward one another, eventually merging into a new, even more massive black hole. This union will release colossal amounts of energy, perhaps in the form of high-energy jets that will illuminate the merging galaxies. Yet, the fate of our solar system during this cosmic ballet is uncertain. As the merger progresses, the Sun and its planets could be ejected to a new and distant region within the resulting galaxy, far from the galactic core. Alternatively, they might remain undisturbed, continuing their orbit much like they do today. However, by the time the Milky Way and Andromeda merge, the Sun will have already entered the final stages of its life cycle. It will swell into a red giant, shedding its outer layers to leave behind a cooling white dwarf. The changes to our solar system are inevitable, but the exact details of how they will play out remain a mystery. Beyond the Milky Way-Andromeda merger, the fate of Milkomeda will be shaped by dark energy, the mysterious force accelerating the expansion of the universe. As galaxies in the larger universe move away from us at increasing speeds, Milkomeda will grow more isolated, cut off from the vast expanse of distant galaxies. Over the course of trillions of years, star formation will grind to a halt as the gas required to form new stars is either used up or expelled. What remains will be a population of aging stars, white dwarfs, neutron stars, and black holes, drifting in the cold, dark universe. This tale of the Milky Way is a powerful reminder of the dynamic, ever-changing nature of the universe. Galaxies are not static. They are not isolated, permanent structures, but are vibrant, evolving systems, constantly merging, breaking apart, and giving birth to new stars and potentially life. In the grand cosmic narrative, our galaxy's story is just one chapter in a much larger book of cosmic evolution, filled with endless possibilities and untold mysteries. Building on this vision of galactic evolution, we now delve deeper into the fundamental process that shapes the structure and fate of the universe, the collision and merger of galaxies. These dramatic encounters are an inevitable consequence of gravitational attraction, pulling galaxies toward one another, sometimes in a slow and graceful cosmic waltz, other times in a chaotic and violent embrace. When two galaxies collide, it is not the stars that directly collide. The vast distances between individual stars within each galaxy mean that collisions between them are exceedingly rare. Instead, it is the gravitational forces at play between the galaxies that dramatically alter their structures. During the initial stage of a merger, the outer halos of the galaxies, composed of dark matter, gas, and stars, begin to interact. These halos exert tidal forces on each other, pulling streams of stars and gas outward, which can lead to bursts of star formation. As the galaxies continue to draw closer, their mutual gravity grows more intense, causing them to oscillate around each other in a slow, graceful dance. As the interaction deepens, the gravitational forces become even more pronounced. The galaxies may pass through one another, their internal structures affected by the close encounter, triggering further bursts of star formation. Over time, this interaction saps the galaxy's relative motion, slowing them down as they lose energy with each pass. This gradual loss of momentum will eventually result in the galaxies coalescing into a single entity. The central supermassive black holes in each galaxy will also begin their journey toward the heart of the new galaxy, drawn together by gravity. In their final moments, these black holes will merge, releasing vast amounts of energy and creating jets of high-energy particles that streak through space, illuminating the newly formed galaxy. The ultimate result of such a merger depends on many factors, including the size, mass, and gas content of the original galaxies. The final galaxy could be an elliptical one, more rounded and with little gas and dust, or it could retain the characteristics of a large spiral galaxy, if enough angular momentum is conserved. The merging process is a slow, monumental event, unfolding over billions of years, shaping the very structure of the universe. In this intricate cosmic dance, galaxies are constantly reshaped and their histories are written in the stars. It is a story of destruction, creation, and evolution, a tale that will continue long after our understanding has evolved, revealing new truths about the universe and our place within it. In the ever-expanding universe, dark matter plays an essential, often unseen role in shaping the cosmos. It is the invisible hand that guides the motion of galaxies, pulling them together and orchestrating the chaotic dance of galactic mergers. As galaxies collide and fuse into one, dark matter is both a participant and a silent architect, influencing their trajectories and ultimately determining the final structure of the merging system. These cosmic collisions, far from being random, are part of the universe's natural rhythm, driving the evolution of galaxies, stimulating star formation, and fostering the intricate interplay of forces that have sculpted the universe over billions of years. When we observe the merging galaxies scattered across the universe, we're not only treated to breathtaking, otherworldly imagery, but also invited to peer deeper into the fundamental processes that govern existence itself. Through these collisions, scientists can observe the behavior of dark matter, witness the gravitational forces at play, and gain critical insights into the life cycle of galaxies. These phenomena do more than just expand our understanding of the cosmos. They provide a glimpse into the dynamic forces that shape the very fabric of reality. But as we venture beyond the immediate confines of the observable universe, a more profound question arises, one that transcends science and delves into the realms of ethics, philosophy, and human curiosity. Should we actively seek to contact extraterrestrial life? This question taps into the essence of what it means to be human, our unrelenting drive to explore, to understand, and to connect with the unknown. For centuries, we have sent spacecraft beyond our planet, sending probes to distant worlds and scanning the vast reaches of space for any sign of life. Yet, the search for extraterrestrial intelligence, SETI, presents us with uncertainties that challenge our very understanding of existence. The idea of reaching out to other civilizations raises profound philosophical and ethical dilemmas. What might we be inviting into our world? Should we continue our quest to find signs of life beyond Earth? Or should we tread cautiously, given the potential risks of contact with far more advanced civilizations? SETI has been an ongoing scientific endeavor for decades, yet even as we listen for signals from the stars, we are faced with an uncomfortable question. What will we do if we receive an answer? Humanity has sent messages into space, hoping that one day we will connect with other intelligent beings. But this endeavor is fraught with risks, both known and unknown. Proponents of the search argue that the discovery of extraterrestrial life would revolutionize our understanding of the universe. It could lead to an unprecedented exchange of knowledge, sparking technological and scientific advancements that could solve some of our most pressing challenges on Earth. The potential to learn from another civilization could illuminate new paths in medicine, physics, and even ethics, revealing insights that could transform life as we know it. The very idea of connecting with another form of intelligence is alluring, offering an opportunity to answer age-old questions about our place in the universe. Yet this pursuit is not without its risks. History has shown us that encounters between civilizations of vastly different technological capabilities can have catastrophic consequences. The discovery of extraterrestrial civilizations far more advanced than us could introduce unforeseen dangers with profound consequences for our species. Would we be able to protect ourselves from technological exploitation, or worse, from an alien species that sees no value in our existence? These concerns are amplified by the unpredictability of what alien life forms might look like, biologically, culturally, and even morally. The vastness of the universe suggests that life elsewhere could be radically different from anything we can imagine, making communication, understanding, and cooperation a monumental challenge. Ethically, the question becomes even more complex. Do we have the right to initiate contact with beings who may have no concept of us or of life as we know it? Without a global consensus, should humanity take such a monumental step? The potential for unintended consequences, whether on Earth or for any extraterrestrial civilizations, raises troubling ethical questions. In our pursuit of knowledge, must we weigh the potential harm of initiating contact with beings whose intentions or values remain a mystery? Philosophically, the question of whether we should reach out to the stars speaks to our very nature. It is an expression of our collective yearning to understand, to explore, and to find meaning in the universe. But it also requires us to confront the responsibility that comes with such a monumental endeavor. It forces us to ask, what are the implications of reaching out into the unknown, not just for us, but for all of humanity and any beings we may encounter? The search for extraterrestrial life forces us to consider the ethical weight of discovery and the profound consequences of connecting with someone other than ourselves. As we move further into the vast expanse of space, it is impossible not to be struck by the sheer scale of the universe. Each galaxy we discover is home to billions of stars, many of which are surrounded by planets, some of which could harbor life. The sheer enormity of space forces us to reassess our own place in the cosmos. We are but a tiny speck, a fleeting moment in the history of the universe, and this realization compels us to reflect on the fragility and preciousness of life on Earth. The vastness of space highlights our insignificance within the cosmic landscape. Yet, it also serves as a reminder of the extraordinary conditions that have allowed life to flourish on Earth. As we contemplate our tiny existence amidst the boundless void, we are forced to question the meaning of life itself. What does it mean to be human in such an expansive, indifferent universe? And what responsibility do we bear, not just to ourselves, but to the entire biosphere that sustains us? In this contemplation, we find ourselves not only questioning the nature of life and intelligence in the universe, but also reconsidering the very meaning of our existence. Are we alone in this grand, infinite universe? Or is our search for extraterrestrial life an expression of something deeper, our desire to understand, to connect, and to find meaning in a world that is, in many ways, incomprehensible? Simultaneously, the vastness of the universe and the intricacy of its design spark awe and wonder, fueling a profound sense of curiosity that drives both scientific and philosophical exploration. The cosmic mystery we seek to unravel is a testament to humanity's resilience and our unyielding thirst for knowledge. Each discovery encourages us to push beyond the limits of our cognitive and technological capabilities, not only to decode the universe's secrets, but also to probe the deepest realms of human consciousness and stretch the boundaries of reason. This journey of discovery challenges us to question what lies beyond the veil of our understanding, urging us to contemplate not just the fabric of the cosmos, but the essence of our very existence. In this pursuit, the possibility of other life forms, scattered across the vast expanse of distant galaxies, compels us to examine the universality of fundamental concepts like consciousness, morality, and the search for meaning. The very notion that we might not be alone raises profound questions about communication and understanding between radically different forms of life. How would our moral frameworks evolve when faced with entities unlike ourselves? How would we reshape our understanding of rights and interconnectedness? The discovery of extraterrestrial life, should it come to pass, would not just transform our scientific worldview. It would revolutionize our philosophical and ethical structures, challenging the anthropocentric narratives that have long defined our place in the world. On a deeper, existential level, the sheer scale of the universe confronts us with the finitude of our existence. It forces us to grapple with questions about the origins and ultimate fate of the universe, the nature of time, and our role within this vast, unfolding drama. To realize that the universe has existed for billions of years before us and will persist for billions more after we are gone can prompt a profound search for meaning and purpose. This realization extends beyond the individual, evoking reflections on legacy, memory, and the enduring impact of our actions, both on future generations and the cosmos itself. However, as we turn our gaze to the stars, we must also ask, How do we reconcile the cost of space exploration with the pressing needs of our own planet? This question lies at the heart of the ongoing debate over how we balance the awe-inspiring potential of space exploration with the immediate demands of Earth's survival. In the quest to venture beyond our world, whether it be through manned missions to the Moon and Mars, or launching probes to the furthest reaches of our solar system, we are confronted with difficult choices. Space exploration is an endeavor that demands significant investment, financial, technological, and human. But the rewards of such endeavors are undeniable: technological innovations, scientific breakthroughs, and a deeper understanding of our place in the cosmos. These discoveries can ripple through society, yielding unforeseen advancements and expanding the horizons of human possibility. At the same time, the challenges we face on Earth are immense. Climate change, poverty, disease, and dwindling resources demand our immediate attention. The juxtaposition of funding space exploration against the backdrop of these urgent issues raises critical ethical and practical concerns. How do we prioritize where to allocate limited resources? It's a dilemma that requires a thoughtful, forward-looking approach. However, the reality is that the pursuit of space and the care for Earth need not be mutually exclusive. In fact, they can complement each other. Technological innovations born from space missions have already made a profound impact on life on Earth. Satellite communications, GPS technology, and advances in materials science have revolutionized everything from disaster response to environmental monitoring. Similarly, the exploration of space can provide insights that help us address challenges right here on Earth. Studies of other planets, particularly Mars and Venus, offer critical data on climate change and environmental degradation, providing lessons that could inform our stewardship of Earth's ecosystems. The search for life beyond Earth underscores the rarity and fragility of our own biosphere, heightening the urgency of preserving the planet's biodiversity. Moreover, a sustainable approach to space exploration involves global cooperation. As nations unite in shared missions, the financial burden and rewards of discovery can be distributed more equitably. International collaboration fosters a sense of shared purpose, transcending geopolitical divides and uniting humanity in the pursuit of knowledge and the preservation of our home planet. Through such cooperation, space exploration can become a unifying force, one that brings us together to explore the unknown while ensuring we remain responsible caretakers of Earth. As we close this chapter, we turn our attention to a question that captivates the imagination of humankind. How close are we to discovering life on other planets? This question lies at the intersection of several scientific disciplines, from astronomy to biology, and it has driven our collective curiosity for centuries. The search for extraterrestrial life has taken great strides, propelled by technological advancements and an enhanced understanding of where and how to search. At the heart of this quest lies the study of exoplanets, planets orbiting stars outside our solar system. Some of these exoplanets reside within their star's habitable zone, where conditions might allow for liquid water to exist on their surfaces. Thanks to groundbreaking missions such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey satellite TESS, thousands of exoplanets have been cataloged, including several Earth-sized worlds within the habitable zone of their respective stars. These discoveries offer a tantalizing glimpse into a universe teeming with potential for life. In the coming years, the James Webb Space Telescope, JWST, will take this search to a new level. With its advanced infrared capabilities, JWST will be able to peer into the atmospheres of these distant worlds, searching for chemical signatures of life, such as oxygen, methane, and water vapor, that could indicate the presence of biological activity. Simultaneously, our own solar system offers another avenue for discovery. Mars, with its past evidence of water, remains one of the most promising candidates for hosting life, whether past or present. NASA's Perseverance rover and the European Space Agency's ExoMars rover are already on the ground, scouring the Martian surface for signs of life. Meanwhile, the icy moons of Jupiter and Saturn, Europa, Enceladus, and Titan, are thought to harbor subsurface oceans, which could provide the ideal conditions for life. Missions like Europa Clipper and the proposed Enceladus Life Finder are poised to explore these alien seas, potentially unlocking the secrets of life beyond Earth. Thus, the quest for extraterrestrial life continues, a journey that blends the frontiers of science with the timeless questions that have always driven us. Are we alone, and what does our place in the universe truly mean? The answers, as we continue to explore, may yet change everything we know about ourselves and our world. Despite the monumental strides we have made in the field of space exploration, the discovery of life beyond Earth remains an elusive and tantalizing prospect. The vast distances that separate us from potential habitable worlds are one of the greatest obstacles in our quest for extraterrestrial life. Direct exploration of distant planets and moons seems like a dream far off in the future, a journey that will require more time, innovation, and technological progress than we can currently fathom. Yet, even with the limits of our current technology, the yearning to understand the cosmos and to uncover the mysteries of life beyond our planet propels us forward into uncharted territories. At the heart of this quest lies a fundamental challenge. Our understanding of life is inherently biased by our Earth-centric perspective. All our research and exploration methods are based on the biology and life forms we know, life as we see it here on Earth. But what if life elsewhere does not adhere to these familiar patterns? It may take forms that are entirely alien to our current knowledge, and this requires us to broaden the definitions we use for life, as well as the ways in which we search for it. This complexity forces us to rethink the very essence of what it means to be alive. To uncover these cosmic secrets, our future efforts must be defined by an openness to the unknown, along with the ingenuity to detect life in forms we cannot yet imagine. As we contemplate our future journey into the stars, it's clear that the pathway to discovering life on distant planets is inextricably linked to technological advancements. These innovations will refine our current exploration capabilities while simultaneously unlocking new frontiers of scientific inquiry. However, the key to pushing the boundaries of our exploration lies in overcoming the fundamental limitations of our technology. The goal of reaching distant star systems, studying exoplanets in exquisite detail, and possibly even discovering extraterrestrial life requires nothing less than groundbreaking advancements across multiple technological domains. One of the most exciting areas of advancement is in propulsion technology. Current spacecraft propulsion systems are confined by the speeds they can achieve, rendering interstellar travel virtually impossible within the span of human lifetimes. Concepts such as ion drives, nuclear thermal propulsion, and the more speculative ideas like antimatter engines and warp drives represent the cutting edge of propulsion research. If these technologies mature, they could one day enable us to travel vast distances and reach distant star systems in a fraction of the time currently imaginable. Moreover, light sail technology, which relies on laser beams to propel spacecraft at significant fractions of the speed of light, offers a tantalizing glimpse into the future. This could pave the way for interstellar probes capable of traveling to neighboring star systems, opening up new realms of exploration far beyond the reach of current propulsion methods. Equally important to these advancements in propulsion are the developments in telescope and observation technology. The James Webb Space Telescope, launched with much anticipation, marks a monumental leap in our ability to explore the cosmos. But this is just the beginning. The future promises even greater innovations in observation technology, such as the creation of extremely large telescopes both on Earth and in space. Equipped with advanced adaptive optics to correct for atmospheric distortions, these telescopes will be capable of imaging exoplanets directly, perhaps even revealing surface details of worlds light years away. Furthermore, new technologies in interferometry, where light from multiple telescopes is combined to enhance resolution, will allow us to study the chemical compositions of distant planets' atmospheres, searching for subtle signs of biosignatures, the telltale signs of life. Another frontier that will be pivotal in our quest for knowledge is the role of robotics and automation. As we venture farther into the solar system and beyond, human presence becomes increasingly impractical. The need for autonomous spacecraft capable of making real-time decisions without waiting for instructions from Earth will become paramount. Advances in artificial intelligence, AI, and machine learning will enable these probes and rovers to navigate treacherous landscapes, carry out complex scientific experiments, and adapt to unexpected situations, all without human intervention. With these developments, we'll be able to send spacecraft to distant, hard-to-reach places and carry out detailed studies of alien worlds in ways that were once impossible. In addition to these developments in autonomy, the miniaturization of technology is opening up new possibilities for exploration. CubeSats and nanosatellites, small, low-cost platforms, are becoming increasingly prevalent in space missions. These tiny, yet powerful satellites can be deployed in large numbers, offering an affordable way to study cosmic phenomena, monitor asteroids, or even facilitate interplanetary communications. Their versatility and cost-effectiveness make them ideal tools for space missions, allowing for a broader and more expansive exploration of the universe. Finally, as we push farther into space, the sustainability of our missions will be crucial. Long-duration trips to Mars and beyond require robust life support and habitat systems to keep astronauts alive and healthy. Technologies that allow us to recycle air, water, and waste will be essential for future missions, ensuring that astronauts can survive for extended periods in the harsh environment of deep space. Additionally, innovations in habitat technology, such as protective shields against cosmic radiation and extreme temperatures, will be critical for safeguarding human life on distant worlds. These advancements will be essential not only for maintaining the well-being of spacefarers, but also for ensuring the long-term viability of human exploration beyond Earth. In this race toward understanding the universe and potentially discovering life elsewhere, we stand on the precipice of a new era. The journey to explore the cosmos will demand innovation, collaboration, and dedication across a multitude of scientific disciplines. And while the path may be long and filled with unknown challenges, the rewards, an expanded understanding of life, the universe, and our place within it, will be well worth the effort. In the not-so-distant future, the advancement of in-situ resource utilization, ISRU techniques, could reshape our understanding of what it means to live beyond Earth. By extracting and utilizing resources from the Martian soil or asteroids, we may lay the groundwork for sustainable colonies on Mars and other celestial bodies. This technological leap will be a key enabler for humanity to not only explore, but also thrive in space, making off-Earth living a reality. Yet, as we venture into the unknown, a question emerges that stirs both scientific curiosity and philosophical wonder. What message would we, as humans, choose to send to an extraterrestrial civilization? This question is not simply about the practicalities of interstellar communication. It is a profound reflection on who we are as a species, on the essence of our identity, our achievements, and our collective aspirations. Creating a message for extraterrestrial beings is an exercise in distilling the complex narrative of human existence into something universally comprehensible. It is a task that demands we reflect on the very nature of what it means to be human. Our desires, struggles, hopes, and dreams. What aspects of our world do we want to share, and which universal truths could we communicate that transcend the boundaries of space, time, and culture? At the heart of this message, we might begin with the universal language of mathematics and the fundamental physical laws that govern the universe. These principles are likely to be constants across the cosmos, offering a shared foundation for understanding. Through mathematical formulas, we could introduce the structure of the atom, the nature of light, and the principles of energy, establishing a common ground for communication. Visual representations, perhaps diagrams of atoms, stars, and galaxies, could serve as a bridge, allowing distant civilizations to decipher our message. Yet, the scope of our message would not be confined to the scientific. It would also reflect the richness and diversity of life on Earth. We could share images of our planet's biosphere, from the tiniest microorganisms to the sprawling landscapes of forests and oceans, teeming with life. This portrayal of Earth's ecosystems would offer a glimpse into the complexity of life that has evolved over millions of years, a testament to the beauty and resilience of our world. Music and art, as expressions of our shared humanity, would be key elements in conveying our culture. These forms of communication speak to the universal emotions and ideas that unite us all. We might choose pieces of music that evoke a range of human emotions, from joy to sorrow, hope to longing. These, like the visual images of Earth's landscapes, would serve as a universal language of the human experience, one that transcends linguistic barriers. In addition to art, greetings in multiple languages could offer a glimpse into the rich tapestry of human cultures. Expressions of peace, goodwill, and the desire for friendship would be central to our message. This would not just be a communication of knowledge, but a gesture of friendship, a wish to bridge the gap between species, if such beings exist, and to establish peaceful relations across the stars. Equally important, the message could include reflections on the ethical principles that guide human society. Our commitment to understanding the universe, our desire for exploration, and our responsibility to protect the planet and all life forms that inhabit it would be integral to the narrative. These aspirations are not just goals, they are reflections of our collective conscience and our deepest moral values. By sharing them, we convey the essence of what it means to be human. Ultimately, the message to an extraterrestrial civilization would be an invitation, a declaration of our existence, a statement of our journey through time and space, and a wish for connection. It would symbolize our desire to share our story with the cosmos and to reach out across the vastness of space, extending a hand of peace to any who might be listening. As we stand at the edge of a new era in space exploration, we find ourselves contemplating the vastness of the universe and our place within it. Our telescopes, satellites, and space probes have brought us closer to understanding the universe's fundamental laws and its most profound mysteries. We have discovered that the cosmos is far more complex and wondrous than we ever imagined. Yet, as we look outward, we are also compelled to look inward, to reflect on our own identity as a species and our shared destiny. The universe, with its billions of galaxies, its dark matter, and its potential for life beyond Earth, challenges our deepest questions about existence. It beckons us to explore, to ask, and to seek answers to questions that may forever remain beyond our reach. What lies beyond the observable universe? Could there be civilizations out there waiting to make contact? And what does the future hold for humanity in this vast, mysterious cosmos? As we ponder these questions, we also consider the next chapter of our story, a chapter that has yet to be written. The possibilities are as infinite as the stars themselves, filled with mystery, adventure, and hope. What role will humanity play in this grand cosmic narrative? Will we reach out to the stars, or will the stars reach out to us? As we continue our journey through the cosmos, we are reminded of the profound responsibility that comes with exploration. The knowledge we seek may forever change our understanding of life, the universe, and our place in it. The future, filled with both excitement and uncertainty, calls to us, urging us to take the next step into the unknown. What do you think lies beyond our universe? Share your thoughts below, and don't forget to subscribe to our channel Starflux for more on this incredible journey through space and time.